There's a silence out there, so deep, so endless it almost feels alive. A black ocean with no shore, no end, only questions. How far could we really go? For centuries we looked up, caged to Earth by gravity and fear. But rockets shattered that cage. We walked the moon. We sent metal hearts to Mars. Voyager now drifts through interstellar space, carrying whispers of humanity beyond our solar system. Yet even that is barely a step. The nearest star, over 4 light years. With current tech, it'd take tens of thousands of years to reach. But space doesn't care about our dreams. It stretches on, cold and infinite, daring us to chase it. The question isn't if we'll go farther, it's whether we'll survive what lies beyond. The edge of our solar system is not a clear-cut boundary, but rather a complex region where the sun's influence gradually gives way to interstellar space. This transitional area is known as the heliosphere, a vast bubble-like structure created by the solar wind. The outer limits of the heliosphere are marked by several key features. The termination shock is where the solar wind slows down dramatically as it encounters resistance from interstellar material. Beyond this lies the heliosheath, a turbulent region where the solar wind is compressed and heated. Finally, there's the heliopause, considered by many scientists to be the true outer edge of our solar system. The heliopause is where the outward pressure of the solar wind balances with the inward pressure of the interstellar medium. This boundary fluctuates and is roughly 100 astronomical units from the Sun, or about 4 times the distance to Neptune. Beyond the heliopause lies interstellar space, filled with gas, dust, and cosmic rays from other stars. Recent explorations by NASA's Voyager spacecraft have provided valuable data about these outer regions. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space, followed by Voyager 2 in 2018. These missions continue to expand our understanding of the solar system's edge and the vast cosmos beyond. The Sun's influence reaches far beyond the visible planets of our solar system, extending into the depths of space in a vast bubble known as the heliosphere. This region marks the boundary where the solar wind, a stream of charged particles constantly flowing from the Sun, interacts with the interstellar medium. The outer edge of the heliosphere, called the heliopause, lies approximately 14 billion kilometers from the Sun. This is about twice the distance to Pluto, our solar system's most famous dwarf planet. At this enormous distance, the pressure of the solar wind becomes equal to the pressure of the interstellar medium, creating a complex boundary region. Within the heliosphere, the Sun's magnetic field and solar wind dominate, shaping the environment and affecting everything from the orbits of comets to the protection of planets from cosmic radiation. This protective bubble shields our solar system from some of the harsh radiation of interstellar space, playing a crucial role in making life on Earth possible. Beyond the heliopause lies interstellar space, where the influence of other stars begins to take precedence. However, the Sun's gravitational influence extends even further, affecting the orbits of distant comets in the Oort cloud, which may lie as far as 2 light-years from the Sun. The Oort cloud is a vast, spherical region surrounding our solar system, composed of countless icy bodies ranging from small comets to larger planetesimals. Named after Dutch astronomer Jan Oort, who first proposed its existence in 1950, this distant realm marks the outer boundary of our Sun's gravitational influence. Stretching far beyond the orbit of Neptune and the Kuiper belt, the Oort cloud begins at roughly 3,000 astronomical units from the Sun. To put this in perspective, 1 astronomical unit is the average distance between Earth and the Sun. The cloud extends outward to about 100,000 astronomical units, or nearly 1 light-year. At its farthest reaches, the Oort cloud approaches the distance of our nearest stellar neighbor, Proxima Centauri. This immense scale means that objects in the outer regions of the cloud are so weakly bound to our Sun that they can be easily influenced by the gravitational pull of passing stars or other celestial bodies. Scientists believe the Oort cloud contains trillions of icy objects, remnants from the early formation of our solar system. These bodies occasionally get disturbed and fall toward the inner solar system, becoming long-period comets that we can observe from Earth. The vast majority of the Oort cloud, however, remains a mysterious and largely unexplored frontier of our cosmic neighborhood. Our current spacecraft technology, while impressive, still faces significant challenges when it comes to traversing the vast distances of our solar system. The edge of the solar system, often considered to be the heliopause where the solar wind meets interstellar space, lies approximately 11 billion miles from the Sun. The fastest spacecraft we have sent into space so far is NASA's Parker Solar Probe. Launched in 2018, it reached a top speed of about 430,000 miles per hour as it swooped close to the Sun. However, this extreme velocity is not sustained throughout its journey. If we consider a more typical interplanetary spacecraft like Voyager 1, which has actually reached interstellar space, the journey takes considerably longer. Voyager 1, launched in 1977, took approximately 35 years to cross the heliopause. It continues to speed through space at about 38,000 miles per hour. Given our current technology, a spacecraft launched today would likely take at least 3 decades to reach the edge of our solar system. However, new propulsion technologies being developed, such as ion drives and potential future nuclear propulsion, could significantly reduce this travel time in the coming years, bringing the outer reaches of our cosmic neighborhood a bit closer to our grasp. Exploring the far reaches of our solar system presents numerous challenges for space agencies and scientists. The vast distances involved make communication with spacecraft increasingly difficult and time-consuming. Signals from Earth can take hours to reach probes in the outer solar system, requiring careful planning and autonomous systems for spacecraft operations. Power generation becomes a significant hurdle as spacecraft venture farther from the Sun. Solar panels become less effective, necessitating the use of alternative power sources like radioisotope thermoelectric generators. These power constraints limit the capabilities of instruments and communication systems on board the spacecraft. The extreme cold of deep space poses another obstacle. Temperatures plummet to near absolute zero, requiring sophisticated thermal management systems to protect sensitive equipment. Additionally, the sparse distribution of celestial bodies in the outer solar system means that opportunities for gravity assists and course corrections are limited, demanding precise navigation and propulsion techniques. Lastly, the sheer duration of these missions presents unique challenges. Outer solar system exploration can span decades, requiring long-term commitment from space agencies and multi-generational teams of scientists and engineers. This extended time frame also increases the risk of equipment failure or degradation, emphasizing the need for robust and redundant systems in spacecraft design. Our understanding of the solar system's boundaries has evolved dramatically over the centuries. Ancient astronomers believed the solar system extended only as far as Saturn, the farthest planet visible to the naked eye. This view persisted until the late 18th century when William Herschel discovered Uranus, expanding the known limits of our cosmic neighborhood. The discovery of Neptune in the mid-19th century pushed these boundaries even further. For many years, Pluto, discovered in 1930, was considered the outermost planet, defining the edge of our solar system. However, the reclassification of Pluto as a dwarf planet in 2006 marked a significant shift in our understanding. Today, we recognize that the solar system extends far beyond the orbit of Neptune. The Kuiper Belt, a region of icy bodies including Pluto, stretches from about 30 to 50 astronomical units from the Sun. Beyond this lies the scattered disk, extending to about 100 astronomical units, containing objects in highly elliptical orbits. Even more distant is the Oort cloud, a theoretical sphere of icy bodies surrounding our solar system. While not directly observed, the Oort cloud is believed to extend up to 100,000 astronomical units from the Sun, marking the current estimated boundary of our solar system. This vast expansion of our understanding showcases how technological advancements and new discoveries continue to reshape our cosmic perspective. The heliosphere acts as a protective bubble around our solar system, shielding us from the harsh environment of interstellar space. This vast region is created by the sun's solar wind, a constant stream of charged particles flowing outward in all directions. As these particles travel through space, they push against the interstellar medium, carving out a cocoon-like shape that extends far beyond the orbit of Pluto. Within the heliosphere, the solar wind's influence dominates, creating a unique environment distinct from the surrounding galaxy. This bubble helps regulate the amount of cosmic radiation that enters our solar system, providing a measure of protection for Earth and other planets. The boundary where the heliosphere meets interstellar space is called the heliopause, marking the edge of our sun's direct influence. The heliosphere is not static but constantly changing in response to variations in solar activity. During periods of increased solar output, the heliosphere expands, pushing its boundary farther into space. Conversely, when solar activity decreases, the heliosphere contracts, allowing more cosmic radiation to penetrate our cosmic neighborhood. By defining the extent of the sun's influence, the heliosphere effectively marks the boundary of our solar system. It serves as a transition zone between the familiar realm of our star and planets and the vast, mysterious expanse of interstellar space that lies beyond. Studying the farthest regions of our solar system presents unique challenges due to the vast distances involved. Scientists employ a variety of sophisticated tools and techniques to explore these remote areas. Space probes and telescopes play crucial roles in our understanding of the outer solar system. Robotic spacecraft, like New Horizons, have been sent on long journeys to capture close-up images and gather data from distant planets and their moons. These missions often take years or even decades to reach their destinations. Once there, they use specialized instruments to measure factors such as temperature, atmospheric composition, and magnetic fields. Ground-based and space-based telescopes also contribute significantly to our knowledge. Advanced optical systems and radio telescopes can detect faint signals from distant objects, revealing information about their size, composition, and behavior. The Hubble Space Telescope, for instance, has provided detailed images of Pluto and other distant bodies. Computer modeling and data analysis complement these observational methods. Scientists use powerful computers to process the vast amounts of information collected, helping to create detailed models of distant worlds and predict the behavior of objects in the outer solar system. This combination of direct observation and computational analysis allows us to study and understand regions of our solar system that lie billions of kilometers from Earth. Our exploration of the solar system's outer reaches has revealed a realm far more dynamic and complex than once imagined. The discovery of the Kuiper Belt, a vast region beyond Neptune teeming with icy bodies, dramatically expanded our understanding of the solar system's structure. This region, home to Pluto and countless other dwarf planets and smaller objects, hints at the solar system's turbulent past and ongoing evolution. Perhaps one of the most intriguing findings is the presence of organic compounds on many of these distant bodies. Pluto, once considered a barren ice ball, has shown signs of a subsurface ocean and complex surface geology, including ice mountains and nitrogen glaciers. This unexpected complexity challenges our notions of what constitutes a living world and expands the potential for habitable environments in the cosmos. The Voyager missions, now venturing into interstellar space, have encountered the heliosphere, the bubble of charged particles from the sun that defines the boundary of our solar system. The shape and behavior of this boundary have surprised scientists, revealing a more dynamic interaction between our star and the surrounding interstellar medium than previously thought. These discoveries at the fringes of our cosmic neighborhood continually reshape our understanding of planetary formation, the distribution of elements throughout the solar system, and the potential for life beyond Earth. As we push further into this frontier, each new finding seems to raise more questions than it answers, driving our curiosity and exploration ever outward. Beyond the Kuiper Belt, we venture into the outer reaches of our solar system, where the influence of our sun begins to wane. This distant region is known as the Oort cloud, a vast sphere of icy bodies that surrounds our planetary system. Unlike the relatively flat disk of the Kuiper belt, the Oort cloud forms a giant bubble around the Sun, extending nearly halfway to the nearest star. The Oort cloud is thought to contain trillions of comets, ranging in size from small rocks to bodies larger than mountains. These objects are remnants from the formation of our solar system, preserved in a deep freeze far from the Sun's warmth. It's from this region that long-period comets originate, taking thousands of years to complete a single orbit around the Sun. Between the Kuiper belt and the Oort cloud lies a sparsely populated area called the scattered disk. This region contains icy bodies that have been gravitationally scattered by the influence of Neptune and the other giant planets. Notable objects in this area include Eris, once considered for classification as the 10th planet. As we push beyond the Oort cloud, we enter interstellar space, the vast void between star systems. This marks the edge of our Sun's gravitational influence and the beginning of true deep space, where the distances between objects become almost incomprehensibly large. The closest star system to our own is Alpha Centauri. This neighboring stellar family lies just over 4 light-years away from Earth, making it our cosmic next-door neighbor in the vastness of space. Alpha Centauri is not a single star, but a system composed of 3 stars orbiting each other. The 2 main stars in this system are Alpha Centauri A and Alpha Centauri B. These stars are similar to our Sun in size and brightness, and they orbit each other every 80 years. The third member of this stellar trio is a small, dim red dwarf star called Proxima Centauri. Despite being part of the Alpha Centauri system, Proxima Centauri is actually the star that sits closest to Earth at a distance of about 4.2 light-years. Proxima Centauri has garnered significant attention from astronomers and exoplanet hunters in recent years. In 2016, scientists discovered an Earth-sized planet orbiting within Proxima Centauri's habitable zone, the region around a star where liquid water could potentially exist on a planet's surface. This planet, named Proxima Centauri b, has since become a prime target in the search for potentially habitable worlds beyond our solar system. The Alpha Centauri system serves as a constant reminder of the wonders that lie just beyond our cosmic doorstep. As our closest stellar neighbors, these stars continue to captivate scientists and space enthusiasts alike, offering tantalizing possibilities for future exploration and discovery in our galactic backyard. With our present spacecraft technology, a journey to Alpha Centauri would be an incredibly lengthy endeavor. The fastest spacecraft we have built to date, the Parker Solar Probe, can reach speeds of about 400,000 miles per hour. Even at this remarkable velocity, it would take the probe over 5,000 years to reach our nearest stellar neighbor. To put this into perspective, if we had launched such a spacecraft during the construction of the Great Pyramids of Giza, it would still be traveling through the vast emptiness of space today, with millennia left in its journey. This immense timescale highlights the true scale of interstellar distances and the limitations of our current propulsion systems. However, scientists and engineers are actively working on developing more advanced propulsion technologies that could significantly reduce travel times. Concepts like nuclear propulsion, antimatter engines, and light sails powered by lasers offer the potential to reach a fraction of the speed of light, potentially cutting the journey time to decades rather than millennia. Despite these challenges, the allure of reaching Alpha Centauri remains strong. The star system potentially hosts habitable planets and holds secrets about the formation and evolution of solar systems beyond our own. As our technology advances, the dream of interstellar travel inches closer to reality, though it remains one of humanity's greatest challenges. Interstellar travel presents numerous formidable challenges that push the boundaries of our current scientific and technological capabilities. The vast distances between stars pose the most significant obstacle. Even our closest stellar neighbor, Proxima Centauri, is over 4 light-years away, meaning it would take 4 years to reach it traveling at the speed of light, which is currently impossible for any spacecraft. The immense energy requirements for interstellar journeys are another major hurdle. Accelerating a spacecraft to even a fraction of light speed would require enormous amounts of fuel, far beyond our current propulsion technologies. Additionally, the spacecraft would need to carry enough fuel for deceleration upon reaching its destination, further compounding the energy problem. Protecting human crew members during such long journeys is another critical challenge. Prolonged exposure to cosmic radiation and microgravity can have severe health effects. Developing effective shielding and artificial gravity systems, as well as addressing psychological issues of isolation and confinement, are essential for crewed missions. Lastly, the need for self-sustaining life support systems for potentially decades-long journeys presents significant engineering challenges. These systems must reliably provide air, water, food, and waste management for the entire duration of the mission with minimal outside resources. Overcoming these obstacles will require substantial advancements in multiple scientific and technological fields. The immense distances between celestial bodies in space present significant challenges for long-distance travel. These vast expanses, often referred to as the vacuum of space, are not entirely empty but contain extremely low densities of matter, primarily hydrogen atoms. This near emptiness has both advantages and drawbacks for space travel. On the positive side, the lack of atmospheric resistance allows spacecraft to maintain their velocity without constant propulsion once they reach their desired speed. This principle, known as inertia, means that objects in motion tend to stay in motion in the absence of external forces. However, the sheer scale of these distances poses major obstacles. Even at incredibly high speeds, journeys between planets, let alone stars, can take years or even decades. For example, light from the Sun takes about 8 minutes to reach Earth, and over 4 years to reach the next nearest star system, Alpha Centauri. For spacecraft traveling at much slower speeds, these journeys become exponentially longer. The emptiness of space also presents challenges for human survival during long-distance travel. Spacecraft must be entirely self-contained, providing all necessary life support systems, protection from cosmic radiation, and resources for the duration of the journey. These requirements significantly increase the complexity and cost of long-distance space missions, making them formidable undertakings in our quest to explore the cosmos. A light year is the distance light travels in 1 Earth year. This vast measurement equals about 9.5 trillion kilometers, or nearly 6 trillion miles. Light moves incredibly fast, racing through space at 300,000 kilometers per second. Even at this breakneck speed, it takes light an entire year to cover this enormous distance. Light years are crucial when discussing space travel because they help us grasp the immense scales involved in interstellar journeys. Our nearest stellar neighbor, Proxima Centauri, lies about 4 light-years away. This means that even if we could travel at the speed of light, which is impossible for any object with mass, it would still take 4 years to reach this closest star. The light-year concept also highlights the challenges of long-distance space exploration. Our current spacecraft move much slower than light. The fastest human-made object, the Parker Solar Probe, travels at about 690,000 kilometers per hour. At this speed, a trip to Proxima Centauri would take about 6,500 years. Understanding light years puts into perspective the vast distances between stars and galaxies. It underscores the need for revolutionary propulsion technologies if we ever hope to explore beyond our solar system. The light year serves as a humbling reminder of our place in the cosmos and the monumental task of venturing into deep space. Overcoming the vast distances between stars remains one of the greatest challenges in space exploration. Current spacecraft propulsion systems are far too slow to make interstellar travel feasible within human lifetimes. However, scientists and engineers are exploring several promising technologies that could potentially bridge these cosmic gaps. One approach involves developing advanced propulsion systems like nuclear propulsion or antimatter engines. These could theoretically achieve speeds much greater than our current chemical rockets, significantly reducing travel times between stars. Another concept under consideration is the light sail, which would use the pressure of light from lasers to accelerate a spacecraft to a fraction of the speed of light. More speculative ideas include the theoretical possibility of warp drives or wormholes. These concepts, while currently beyond our technological capabilities, are based on manipulating space-time itself to create shortcuts through the cosmos. Scientists continue to study these ideas, hoping to uncover ways to make them physically possible. In the meantime, researchers are also exploring the potential of generation ships or suspended animation technologies. These approaches would allow humans to survive long journeys between stars, either by living aboard self-sustaining spacecraft for centuries or by slowing down biological processes during transit. While the challenges are immense, the quest to reach other stars continues to drive innovation in space technology. Wormholes represent a fascinating possibility for interstellar travel, offering a potential shortcut through the fabric of space-time. These theoretical tunnels could connect two distant points in the universe, allowing for near instantaneous travel between them. This concept has captured the imagination of scientists and science fiction enthusiasts alike, as it presents a way to overcome the vast distances that separate star systems. In theory, a wormhole could dramatically reduce travel times across the cosmos. Instead of spending years or even centuries traversing the enormous gulfs between stars, a spacecraft might pass through a wormhole and emerge light years away in a matter of moments. This would revolutionize our ability to explore and potentially colonize distant parts of the galaxy. However, the existence of traversable wormholes remains purely theoretical. While they are compatible with Einstein's theory of general relativity, we have yet to observe any in nature. Moreover, even if they do exist, there are significant challenges to using them for travel. Wormholes might be incredibly unstable, collapsing as soon as any matter or energy tries to pass through them. They might also be microscopic in size, far too small for a spacecraft to enter. Despite these challenges, the study of wormholes continues to push the boundaries of our understanding of physics. If we could somehow create or stabilize a wormhole, it would not only revolutionize space travel, but also our comprehension of the fundamental nature of space and time. The role of wormholes in interstellar travel remains a tantalizing possibility that drives scientific inquiry and fuels our dreams of exploring the stars. Warp drives and faster-than-light travel have long captivated the imagination of science fiction enthusiasts, but their feasibility in the real world remains a subject of intense scientific debate. While these concepts are theoretically possible according to some interpretations of physics, they face significant practical and technological hurdles that currently place them firmly in the realm of speculation. The idea of a warp drive, popularized by science fiction, involves manipulating space-time itself to create a bubble of normal space that moves faster than light relative to the rest of the universe. This concept is based on the fact that while nothing can move faster than light through space, space itself can expand or contract at any speed. However, the energy requirements for such a device would be astronomical, potentially requiring more energy than exists in the observable universe. Faster-than-light travel faces similar challenges. According to Einstein's theory of special relativity, as an object approaches the speed of light, its mass increases exponentially, requiring infinite energy to reach light speed. This presents a seemingly insurmountable barrier to traditional propulsion methods. Some theoretical workarounds involve exotic concepts like wormholes or quantum entanglement, but these remain highly speculative and far beyond our current technological capabilities. Despite these challenges, scientists continue to explore these ideas, pushing the boundaries of our understanding of physics. While warp drives and faster-than-light travel may not be realistic in the near future, the pursuit of these concepts drives innovation and expands our knowledge of the universe, potentially leading to unexpected discoveries along the way. Several intriguing methods have been proposed for achieving interstellar travel, pushing the boundaries of our current technological capabilities. One of the most promising concepts is the use of light sails, which harness the power of lasers or solar radiation to propel spacecraft. These ultra-thin reflective sails could potentially accelerate a small probe to a significant fraction of the speed of light, allowing it to reach nearby star systems within decades. Another proposed method involves nuclear propulsion, using either fusion or fission reactions to generate immense thrust. Nuclear pulse propulsion, for instance, would detonate a series of nuclear explosions behind a spacecraft, propelling it forward at high speeds. While controversial, this method could theoretically achieve the velocities needed for interstellar travel. Antimatter propulsion represents an even more advanced concept. By harnessing the enormous energy released when matter and antimatter annihilate each other, a spacecraft could achieve unprecedented speeds. However, the challenges of producing and storing sufficient quantities of antimatter currently make this approach impractical. Lastly, some scientists have proposed more speculative methods, such as warp drives or wormholes, which could theoretically allow faster-than-light travel by manipulating the fabric of spacetime itself. While these concepts are rooted in legitimate physics, they remain highly theoretical and may require exotic forms of matter or energy that we have yet to discover or harness. Sustaining human life during centuries-long space journeys presents numerous challenges that scientists and engineers are working to overcome. One of the primary concerns is providing a stable and renewable food source. Advanced hydroponics and aeroponics systems could allow crews to grow a variety of nutrient-rich plants in controlled environments, supplementing their diet with lab-grown proteins. Recycling will be crucial for long-term survival. Closed-loop life support systems would need to recycle air, water, and waste with near-perfect efficiency. Technologies like algae bioreactors could play a dual role, producing oxygen and food while helping to purify water and air. Protecting astronauts from the harmful effects of prolonged exposure to cosmic radiation is another critical challenge. Potential solutions include developing advanced shielding materials or incorporating radiation-absorbing water tanks into spacecraft design. Some researchers are even exploring the possibility of putting crew members into a state of hibernation or suspended animation to reduce their overall exposure and resource consumption. Maintaining physical and mental health over such extended periods will require innovative solutions. Artificial gravity systems, possibly created through centrifugal force in rotating sections of the spacecraft, could help prevent muscle and bone loss. Virtual reality technologies might be employed to provide mental stimulation and combat the psychological effects of long-term isolation in the vast emptiness of space. Chemical rockets have served as our primary means of space exploration for decades, but they face significant challenges when it comes to deep space missions. The fundamental issue lies in their reliance on chemical reactions to generate thrust. This process requires carrying both fuel and oxidizer, which adds considerable mass to the spacecraft. As we venture further into space, the amount of propellant needed increases exponentially. This creates a vicious cycle where more fuel is required to propel the extra weight of the fuel itself. Consequently, chemical rockets struggle to achieve the high velocities necessary for efficient deep space travel. Another limitation is the finite energy contained within chemical propellants. Even the most efficient chemical reactions release only a fraction of the energy needed for rapid interplanetary or interstellar journeys. This means that missions to distant targets like the outer planets or beyond our solar system would take years or even decades using conventional rocket technology. Furthermore, chemical rockets offer limited control over thrust once in space. They typically operate in short, powerful bursts rather than providing continuous acceleration. This makes it challenging to perform complex maneuvers or make course corrections during long-duration missions, potentially limiting the flexibility and range of deep space exploration endeavors. Ion propulsion is a revolutionary space propulsion technology that uses electricity to accelerate ions to create thrust. This advanced system works by first ionizing a propellant, typically xenon gas, by stripping away electrons. The resulting positively charged ions are then accelerated through an electric field, creating a high-speed exhaust that propels the spacecraft forward. One of the key advantages of ion propulsion is its exceptional fuel efficiency. Compared to traditional chemical rockets, ion engines can achieve much higher specific impulse, meaning they can generate more thrust per unit of propellant. This allows spacecraft to travel farther and faster using less fuel, making ion propulsion ideal for long-duration deep space missions. Another benefit of ion propulsion is its ability to provide continuous thrust over extended periods. While the thrust produced is relatively low, it can be applied for months or even years, gradually building up to significant velocities. This constant acceleration enables spacecraft to reach distant targets that would be impractical or impossible with conventional propulsion methods. Ion engines also offer precise control and maneuverability, allowing for accurate trajectory adjustments and orbital positioning. Their low thrust and high efficiency make them particularly suitable for maintaining the orbits of satellites and space stations, as well as for interplanetary exploration missions where fuel conservation is crucial. Nuclear propulsion is an advanced method of spacecraft propulsion that harnesses the power of nuclear reactions to generate thrust. Unlike conventional chemical rockets, which rely on combustion, nuclear propulsion systems use the heat produced by nuclear fission or fusion to expel propellant at extremely high velocities. This technology is particularly appealing for long-distance space travel due to its potential for high efficiency and sustained acceleration. Nuclear propulsion systems can provide continuous thrust for extended periods, allowing spacecraft to reach higher speeds and cover vast distances more quickly than traditional chemical rockets. One of the main advantages of nuclear propulsion is its high specific impulse, which means it can generate more thrust per unit of propellant consumed. This efficiency is crucial for deep space missions where carrying large quantities of fuel becomes impractical. With nuclear propulsion, spacecraft could potentially reach distant planets or even venture beyond our solar system in significantly less time than current propulsion methods allow. However, nuclear propulsion also presents challenges, including radiation shielding, heat management, and safety concerns. Despite these hurdles, many scientists and engineers view nuclear propulsion as a promising solution for future interplanetary and interstellar missions, potentially opening up new frontiers in space exploration. Antimatter propulsion represents one of the most powerful potential fuel sources for future spacecraft. When matter and antimatter collide, they annihilate each other, releasing an enormous amount of energy. This energy could be harnessed to provide thrust for a spacecraft, offering unparalleled efficiency compared to conventional rocket fuels. The concept involves storing small amounts of antimatter, typically antiprotons, in electromagnetic traps. When needed, these antiprotons would be carefully released to collide with normal matter, producing a controlled stream of high-energy particles. This particle stream would then be directed through a magnetic nozzle, propelling the spacecraft forward. The efficiency of antimatter as a fuel is staggering. A mere gram of antimatter, reacting with a gram of matter, could produce an energy equivalent to that of a 40-kiloton nuclear bomb. This tremendous energy density means that even tiny amounts of antimatter could potentially accelerate a spacecraft to a significant fraction of the speed of light, enabling interstellar travel within human timescales. However, significant challenges remain before antimatter propulsion becomes a reality. Producing and storing antimatter is extremely difficult and costly with current technology. Additionally, the radiation produced by matter-antimatter annihilation poses serious safety concerns that must be addressed. Despite these hurdles, the potential of antimatter as a revolutionary spacecraft fuel continues to captivate scientists and engineers. Solar sail technology harnesses the power of sunlight to propel spacecraft through the cosmos. These innovative sails are made of ultra-thin, reflective materials that capture the momentum of photons streaming from the sun. As light particles bounce off the sail's surface, they transfer their momentum to the spacecraft, gradually accelerating it to impressive speeds. Unlike traditional rockets that require massive amounts of fuel, solar sails offer a fuel-free propulsion method for long-distance space travel. This technology could potentially allow spacecraft to reach distant stars and planets more efficiently than ever before. As the sail continually accelerates over time, it can achieve velocities far beyond what conventional propulsion systems can manage. One of the most exciting aspects of solar sail technology is its scalability. Larger sails can capture more photons, potentially enabling faster travel or the ability to transport heavier payloads. Additionally, advanced designs might use artificial light sources, such as powerful lasers, to provide an extra boost when sunlight becomes too weak in the outer reaches of our solar system. The potential applications of solar sail technology are vast. From interplanetary cargo delivery to deep space exploration missions, this innovative propulsion method could open up new frontiers in our quest to understand the universe. As we continue to refine and improve solar sail designs, we may be witnessing the dawn of a new era in space travel, one that relies on the simple yet powerful force of light to carry us to the stars. As we look to the future of space exploration, several groundbreaking propulsion technologies are showing immense promise. Ion propulsion, which uses electrically charged particles to generate thrust, is already being utilized in some spacecraft and continues to be refined for greater efficiency. This technology offers the advantage of sustained acceleration over long periods, making it ideal for deep space missions. Nuclear thermal propulsion is another exciting prospect. By using a nuclear reactor to heat propellant to extreme temperatures, this method could potentially halve travel times to Mars compared to conventional chemical rockets. While still in development, it represents a significant leap forward in our ability to explore the solar system. Antimatter propulsion, though currently theoretical, holds the potential for unparalleled energy density. The challenge lies in producing and storing sufficient quantities of antimatter. But if achieved, it could revolutionize interstellar travel. Similarly, fusion propulsion, which would harness the power of nuclear fusion reactions, offers the promise of high thrust and efficiency. Lastly, solar sails are gaining traction as a fuel-free propulsion method. These large, lightweight sheets use the pressure of sunlight or laser beams for propulsion, potentially enabling long-duration missions to the outer solar system and beyond. As these technologies continue to advance, they bring us closer to unlocking the vast expanses of space. Fusion drives represent a promising advancement in space propulsion technology. These engines would harness the power of nuclear fusion, the same process that powers stars, to generate thrust for spacecraft. In a fusion drive, lightweight atomic nuclei, such as deuterium or helium-3, would be forced together under extreme heat and pressure, releasing enormous amounts of energy in the process. The energy produced by fusion reactions would be directed out of the spacecraft as exhaust, providing thrust. This method could potentially offer much higher specific impulse than conventional chemical rockets, meaning fusion drives could accelerate for longer periods and reach higher velocities. As a result, spacecraft equipped with fusion drives might be capable of much faster interplanetary travel, significantly reducing journey times to distant planets or even enabling practical interstellar missions. One of the key benefits of fusion drives is their fuel efficiency. The fusion reactions produce far more energy per unit of fuel than chemical combustion, allowing spacecraft to carry less fuel mass. This efficiency could enable longer missions and larger payloads. Additionally, fusion drives would not produce greenhouse gases or other pollutants, making them an environmentally friendly option for space exploration. However, significant technological challenges remain before fusion drives become a reality. Scientists and engineers must overcome issues such as containing the fusion reaction, managing the intense heat generated, and developing materials that can withstand the extreme conditions. Despite these hurdles, ongoing research continues to bring us closer to the day when fusion drives might power our journeys through the solar system and beyond. The Bussard ramjet is a fascinating concept in space propulsion technology. Proposed by physicist Robert Bussard in 1960, this theoretical spacecraft design aims to solve one of the biggest challenges in interstellar travel: the need for enormous amounts of fuel. The key idea behind the Bussard ramjet is to collect its own fuel from the interstellar medium as it travels. It would use an enormous electromagnetic field, potentially thousands of kilometers in diameter, to gather hydrogen atoms scattered sparsely throughout space. These collected atoms would then be compressed and fed into a fusion reactor, providing continuous thrust for the spacecraft. This ingenious design offers the potential for near-constant acceleration over vast distances, theoretically allowing the spacecraft to approach the speed of light. Such capabilities would make interstellar journeys feasible within human timescales, dramatically reducing travel times between stars. However, the Bussard ramjet faces significant technical challenges. The density of hydrogen in interstellar space is extremely low, and the energy required to collect and compress it might exceed the energy produced by fusion. Despite these hurdles, the concept continues to inspire scientists and engineers in their quest for advanced space propulsion methods. Black holes, those cosmic titans of extreme gravity, might seem like unlikely candidates for space propulsion. Yet, their immense power could potentially be harnessed for interstellar travel. One intriguing concept involves using the intense gravitational fields of black holes to accelerate spacecraft to incredible speeds. This method, known as gravitational slingshot or gravity assist, is already used with planets to boost spacecraft velocity. With a black hole, the effect would be magnified exponentially. A carefully plotted trajectory could allow a ship to swing around the black hole, gaining enormous speed in the process. The closer the approach, the greater the potential acceleration, though this would also increase the danger. Another possibility lies in the realm of Hawking radiation, the theoretical emission of particles from a black hole's event horizon. Some scientists propose that advanced civilizations might create and manipulate artificial micro-black holes using the energy from their evaporation as a power source for propulsion. This could provide almost limitless energy for long-distance space travel. However, these ideas remain highly speculative and far beyond our current technological capabilities. The extreme conditions near black holes pose immense challenges for any practical application. Yet as our understanding of these cosmic phenomena grows, so too does the potential for harnessing their awesome power for space exploration. Artificial gravity could revolutionize spacecraft design and long-duration space travel. As missions venture deeper into space, astronauts face significant health challenges from prolonged exposure to microgravity. These include muscle atrophy, bone density loss, and changes in cardiovascular function. Artificial gravity systems could mitigate these issues, allowing humans to live and work in space for extended periods with fewer negative health effects. One proposed method for creating artificial gravity involves rotating a section of the spacecraft. This rotation would generate a centrifugal force that mimics gravity, allowing astronauts to experience a pull similar to Earth's gravitational field. Such a design could incorporate living quarters, exercise areas, and workspaces within the rotating section, while maintaining other parts of the ship in microgravity for specific scientific experiments or operations that benefit from weightlessness. Artificial gravity could also solve practical problems in spacecraft design. It would allow for more Earth-like systems for waste management, food preparation, and personal hygiene. This could simplify many aspects of spacecraft operations and improve the overall quality of life for astronauts on long-duration missions. However, implementing artificial gravity presents significant engineering challenges. The rotating sections would need to be large enough to minimize disorienting effects on the inner ear, and the entire system would require careful balance and control. Despite these hurdles, the potential benefits make artificial gravity a compelling area of research for future space exploration. Time dilation is a fascinating phenomenon predicted by Einstein's theory of relativity. It occurs when time passes at different rates for objects moving at high speeds or experiencing strong gravitational fields. Time slows down for fast-moving objects, or those in strong gravitational fields, compared to stationary objects, or those in weaker fields. For space travel, time dilation becomes a significant factor. As spacecraft accelerate to incredible speeds, time for the astronauts on board slows down relative to Earth. This means that while only months might pass for the space travelers, years could go by on Earth. The effect becomes more pronounced the closer a spacecraft approaches the speed of light. Interestingly, time dilation also affects satellites orbiting Earth. The global positioning system must account for time dilation to maintain accuracy, as the atomic clocks on satellites tick slightly faster than those on Earth due to the weaker gravitational field in orbit. The implications of time dilation for long-distance space travel are profound. It could theoretically allow astronauts to travel vast distances within their lifetimes while centuries pass on Earth. This concept, often explored in science fiction, presents both opportunities and challenges for future space exploration and colonization efforts. Traveling at speeds approaching that of light would dramatically alter an astronaut's experience of time due to a phenomenon known as time dilation. This effect, predicted by Einstein's theory of special relativity, becomes increasingly pronounced as objects move faster through space. For astronauts on a near-light speed journey, time would appear to pass normally from their perspective. However, compared to stationary observers on Earth, the astronauts would age much more slowly. This means that upon returning from their voyage, they might find that significantly more time has elapsed on Earth than they experienced during their trip. The magnitude of this time difference depends on how close to light speed the spacecraft travels. For instance, if astronauts embarked on a 10-year mission at 99.9% the speed of light, they would return to find that about 223 years had passed on Earth. This stark contrast in time progression is often referred to as the twin paradox in discussions of relativity. It's important to note that this effect isn't just theoretical. We observe time dilation in everyday life, albeit on a much smaller scale. Global positioning system satellites, which orbit Earth at high speeds, need to account for time dilation to maintain accuracy. Without these adjustments, GPS systems would quickly become unreliable for navigation. The twin paradox is a fascinating thought experiment in special relativity that challenges our everyday understanding of time. It involves two identical twins, one who stays on Earth and another who embarks on a high-speed journey through space. According to Einstein's theory, time passes more slowly for objects moving at very high velocities. This means the twin traveling through space would age more slowly than the twin remaining on Earth. While it might seem paradoxical at first, this effect has been proven through precise measurements with atomic clocks. The faster-moving twin would indeed return to Earth younger than their Earth-bound sibling. This time, dilation becomes significant only at speeds approaching that of light, which is why we do not notice it in our daily lives. For space exploration, the twin paradox has real implications. Astronauts on the International Space Station, for example, experience time slightly slower than people on Earth. The difference is minuscule for current missions, amounting to only fractions of a second over months in orbit. However, for potential future long-distance space travel at extreme speeds, the effects could become more pronounced. The twin paradox illustrates how space exploration pushes the boundaries of our physical reality. As we venture further into the cosmos, we may need to grapple with the strange consequences of relativity, including time dilation. This could impact communication with Earth, mission planning, and even the aging of space travelers compared to those they left behind. Gravity's influence on time is a fascinating aspect of Einstein's theory of relativity. The stronger the gravitational field, the slower time passes. This means that time moves at different rates depending on where you are in the universe and how much gravity is acting upon you. Near massive objects like black holes or neutron stars, time slows down significantly compared to areas with less gravitational pull. Even on Earth, time passes slightly faster at the top of a tall building than at ground level, though the difference is too small for us to notice in everyday life. This gravitational time dilation becomes crucial for space travel and our understanding of the cosmos. For astronauts on the International Space Station, time moves slightly faster than on Earth's surface due to the weaker gravitational field in orbit. While the difference is minuscule for short missions, it becomes more significant for long-duration space travel or potential journeys to other planets. Space agencies must account for these time differences when designing missions and communication systems. Global Positioning System satellites, for instance, need to adjust for time dilation to maintain accuracy. Without these corrections, GPS navigation would quickly become unreliable. As we venture further into space, understanding and compensating for gravity's effects on time will be essential for precise navigation, communication, and even the well-being of future space travelers. Time dilation, a fascinating consequence of Einstein's theory of relativity, could indeed play a significant role in long-distance space missions. As spacecraft approach the speed of light, time slows down for the travelers compared to those back on Earth. This effect could be harnessed to reduce the subjective duration of extended journeys for astronauts. For instance, a mission to a distant star system might take hundreds of years from Earth's perspective. However, due to time dilation, the crew might experience only a fraction of that time. This could potentially allow humans to explore far-flung regions of space within a single lifetime, at least from the astronaut's point of view. However, time dilation presents complex challenges. While the space travelers might age more slowly, everyone they know on Earth would continue to age at a normal rate. Upon returning from their journey, astronauts could find that centuries have passed on Earth, with profound social and technological changes. Furthermore, achieving the speeds necessary for significant time dilation effects requires enormous amounts of energy, far beyond our current technological capabilities. Despite these hurdles, the concept of using time dilation in space travel continues to captivate scientists and could shape the future of interstellar exploration. Einstein's theories of relativity fundamentally reshape our understanding of space travel, revealing a universe far more complex than we once imagined. Special relativity shows us that as objects approach the speed of light, time slows down for them relative to stationary observers. This time dilation effect means that astronauts on high-speed journeys would experience less time passing than people on Earth, potentially allowing them to travel farther into the future. General relativity, on the other hand, describes how massive objects warp the fabric of space-time. This warping affects the paths of everything moving through space, including light. For space travelers, this means that the shortest path between 2 points is not necessarily a straight line, but rather a curved path, following the contours of space-time. These theories also reveal the immense energy requirements for interstellar travel. As spacecraft approach light speed, they would require exponentially more energy to accelerate further, making it practically impossible to reach or exceed light speed. This limitation poses significant challenges for long-distance space exploration. Moreover, relativity impacts our understanding of navigation in space. The warping of spacetime near massive objects like stars and black holes means that space travelers must account for these distortions when plotting courses across vast cosmic distances. As we venture further into space, Einstein's insights will continue to guide our understanding of the universe and shape the future of space exploration. As a spacecraft approaches the speed of light, it would experience a series of extraordinary effects due to the principles of special relativity. Time for the spacecraft and its occupants would begin to slow down relative to stationary observers on Earth. This time dilation would become more pronounced as the spacecraft's velocity increased, potentially allowing the crew to travel far into the future while aging very little themselves. The spacecraft would also undergo length contraction, appearing shorter along its direction of travel to outside observers. However, the crew inside would not perceive this change. As the ship accelerated closer to light speed, its mass would appear to increase from an external perspective, requiring ever-increasing amounts of energy to achieve further acceleration. Interestingly, the universe would appear to contract from the spacecraft's point of view. Stars and galaxies ahead would shift towards blue in the electromagnetic spectrum, while those behind would redshift. This effect, known as relativistic beaming, would concentrate the ship's view of the universe into a narrow cone ahead of its direction of travel. It is important to note that reaching the exact speed of light is impossible for any object with mass, including a spacecraft. As the ship approaches this cosmic speed limit, the energy required to accelerate further would approach infinity, making light speed an unattainable goal for conventional propulsion methods. Time dilation, a consequence of Einstein's theory of relativity, poses significant challenges for communication during deep space missions. As spacecraft travel at extremely high speeds or experience strong gravitational fields, time passes differently for the astronauts compared to people on Earth. This effect becomes more pronounced the further and faster a spacecraft travels. For missions venturing to distant planets or even beyond our solar system, the time difference could become substantial. Messages sent from Earth might arrive at the spacecraft seemingly faster than expected from the astronaut's perspective, while responses from the spacecraft would appear delayed when received back on Earth. This desynchronization of time could complicate mission planning, data interpretation, and real-time decision-making. Moreover, the vast distances involved in deep space travel already cause significant communication delays due to the finite speed of light. Time dilation would add another layer of complexity to this issue, potentially making it even more challenging to maintain effective two-way communication. Mission controllers and astronauts would need to account for these relativistic effects when coordinating activities and sharing critical information. To address these challenges, future deep space missions might require sophisticated onboard computers capable of autonomously handling many aspects of the mission. Additionally, new communication protocols and technologies may need to be developed to ensure clear, timely, and accurate information exchange between Earth and spacecraft, experiencing significant time dilation effects. Time dilation, a phenomenon predicted by Einstein's theory of relativity, poses fascinating psychological challenges for space travelers. As astronauts journey at high speeds or experience intense gravitational fields, time passes more slowly for them compared to people on Earth. This temporal discrepancy can lead to a profound sense of disconnection and alienation upon their return. Space travelers might find themselves out of sync with loved ones and society, potentially experiencing a form of temporal culture shock. Friends and family would have aged more rapidly, and the world might have changed significantly during what felt like a brief journey to the astronaut. This displacement can trigger feelings of isolation and struggle with reintegration into a society that has moved on without them. Moreover, the awareness of time dilation during space travel could create unique stressors. Astronauts might grapple with the knowledge that for every year they spend in space, multiple years pass on Earth. This realization could lead to anxiety, guilt, or a sense of lost time, impacting their mental well-being and potentially their decision-making processes during missions. The psychological effects of time dilation also extend to the concept of identity and personal continuity. Space travelers might question their place in the timeline of their own lives, struggling to reconcile their subjective experience of time with the objective reality they encounter upon return. This dissonance could challenge their sense of self and require significant psychological adjustment, highlighting the complex interplay between physics, psychology, and human experience in space exploration. Synchronizing time between Earth and distant space colonies presents a fascinating challenge due to the effects of relativity and the vast distances involved. As colonies spread across our solar system and potentially beyond, maintaining accurate timekeeping becomes crucial for communication, navigation, and scientific endeavors. One approach would be to establish a network of highly precise atomic clocks throughout space. These clocks, placed on various planets, moons, and space stations, would form a galactic time system. Each clock would continuously broadcast its time signal, allowing spacecraft and colonies to synchronize their local clocks with this universal standard. However, the time dilation effects of special and general relativity complicate matters. Clocks in different gravitational fields or moving at different velocities will experience time at different rates. To account for this, complex algorithms would need to be developed to adjust for these relativistic effects, ensuring that all clocks remain synchronized regardless of their location or motion. Another potential solution involves using pulsars as natural timekeepers. These rapidly rotating neutron stars emit incredibly regular pulses of radiation. By observing multiple pulsars, colonies could create a cosmic positioning system similar to GPS that provides both location and time information across vast distances. Several key factors contribute to a planet's potential habitability. First and foremost is the presence of liquid water on the surface, which is crucial for life as we know it. This requires the planet to orbit its star within the habitable zone, where temperatures allow water to exist in a liquid state. The planet's size and mass also play vital roles. A world similar in size to Earth is more likely to retain an atmosphere and have the right gravity for life to thrive. Too small, and the planet might lose its atmosphere. Too large, and it could become a gas giant unsuitable for life as we understand it. A stable atmosphere is another critical element. It protects the surface from harmful radiation and helps regulate temperature. The composition of this atmosphere matters too, with a mix of gases that can support potential life forms being ideal. Lastly, the planet's geological activity can be significant. Plate tectonics, for instance, help regulate the carbon cycle and maintain a stable climate over long periods. They also create diverse environments that could foster the evolution of life. While these factors don't guarantee the presence of life, they create conditions where life might potentially develop and flourish. The search for potentially habitable exoplanets has been one of the most exciting endeavors in modern astronomy. As of now, scientists have identified several thousand exoplanets, but only a small fraction of these are considered potentially habitable. Current estimates suggest that we have discovered around 50 to 100 exoplanets that could potentially support life as we know it. These planets orbit within the habitable zone of their stars, where temperatures might allow for liquid water to exist on their surfaces. It's important to note that our definition of potentially habitable is based on Earth-like conditions, which may not be the only form of habitability in the universe. Additionally, our detection methods are still limited, favoring larger planets orbiting smaller stars. This means there could be many more potentially habitable worlds yet to be discovered. As our technology and methods improve, we expect this number to grow significantly in the coming years. Future missions and more powerful telescopes will allow us to detect smaller, more Earth-like planets and even analyze their atmospheres for signs of life. The Goldilocks zone, also known as the habitable zone, is a region around a star where conditions are just right for liquid water to exist on the surface of a planet. This zone is neither too hot, causing water to evaporate, nor too cold, causing water to freeze permanently. The name comes from the fairy tale of Goldilocks, who preferred things that were not too extreme, but just right. The Goldilocks zone is crucial in the search for potentially habitable worlds beyond our solar system. Liquid water is considered essential for life as we know it, making planets within this zone prime candidates for hosting living organisms. The exact boundaries of the habitable zone vary depending on factors such as the star's size, temperature, and the planet's atmosphere. For our Sun, the Goldilocks zone extends roughly from the orbit of Venus to just beyond Mars, with Earth comfortably situated in the middle. This positioning has allowed our planet to maintain liquid water on its surface for billions of years, creating the conditions necessary for life to evolve and thrive. Astronomers use the concept of the Goldilocks zone to focus their search for exoplanets that might support life. By identifying planets orbiting within the habitable zones of their stars, scientists can prioritize targets for further study and potentially discover worlds that could harbor extraterrestrial life. Detecting signs of life on distant planets is a complex and fascinating endeavor that combines cutting-edge technology with scientific ingenuity. Astronomers and astrobiologists use a variety of methods to search for biosignatures, which are indicators of past or present life. One key approach is analyzing the atmospheres of exoplanets. When starlight passes through a planet's atmosphere, certain gases absorb specific wavelengths of light. By studying this spectral data, scientists can identify the presence of gases like oxygen, methane, and carbon dioxide. The simultaneous presence of these gases, especially in certain ratios, could suggest biological activity. Another method involves searching for signs of photosynthesis. On Earth, the abundance of plant life creates a distinctive light reflection pattern known as the red edge. Detecting a similar pattern on other planets could indicate the presence of vegetation or similar light-harvesting organisms. Scientists also look for seasonal changes in atmospheric composition or surface features that might suggest biological cycles. Additionally, they search for technosignatures, such as radio signals or atmospheric pollutants, which could indicate the presence of intelligent life. As our technology advances, we continue to refine these methods and develop new techniques to expand our search for extraterrestrial life. As we explore the cosmos, several intriguing worlds have emerged as potential havens for life beyond Earth. Mars, our rusty neighbor, remains a prime candidate. Despite its current harsh conditions, evidence suggests it once had flowing water and a thicker atmosphere, hinting at past habitability. Subsurface water ice and possible liquid water deposits fuel speculation about microbial life existing today. Venturing further, the icy moons of Jupiter and Saturn captivate scientists. Europa, with its subsurface ocean protected by a thick ice shell, could harbor more liquid water than all of Earth's oceans combined. Enceladus, another icy marvel orbiting Saturn, boasts geysers spewing water vapor and organic compounds, suggesting a potentially life-friendly environment beneath its frozen surface. Titan, Saturn's largest moon, presents a unique case. Its dense atmosphere and liquid methane lakes make it the only celestial body besides Earth known to have stable liquid on its surface. While not water-based, these conditions might support forms of life vastly different from what we know. Beyond our solar system, exoplanets in the habitable zones of their stars offer tantalizing possibilities. Proxima Centauri b, the closest known exoplanet, orbits within the habitable zone of its red dwarf star. The TRAPPIST-1 system, with 7 Earth-sized planets, 3 of which lie in the habitable zone, presents another exciting frontier in the search for potentially life-supporting worlds. Terraforming other planets to make them suitable for human habitation is a complex and ambitious endeavor that scientists have long contemplated. The process would involve dramatically altering a planet's environment to create Earth-like conditions. Mars, our closest planetary neighbor, is often considered the most promising candidate for terraforming. One key aspect of terraforming Mars would be thickening its atmosphere and raising its temperature. This could potentially be achieved by releasing greenhouse gases trapped in the Martian polar ice caps. By warming the planet, we could potentially melt the ice caps, releasing water and carbon dioxide, further accelerating the warming process. Another crucial step would be generating a magnetic field to protect the planet from harmful solar radiation. One proposed method involves placing a large satellite at a specific point between Mars and the Sun to create an artificial magnetosphere. This would help prevent the solar wind from stripping away the newly formed atmosphere. Introducing plant life could also play a vital role in terraforming. Genetically engineered plants adapted to Martian conditions could help produce oxygen and organic material, gradually making the environment more hospitable for humans. However, it is important to note that terraforming is a theoretical concept that would likely take centuries to accomplish, if it is even possible with our current or near-future technology. Moons have emerged as intriguing candidates in our quest for habitable worlds beyond Earth. These natural satellites, often overlooked in favor of planets, offer unique environments that could potentially support life. In our own solar system, moons like Europa, Enceladus, and Titan have captured the attention of scientists due to their promising conditions. Europa, one of Jupiter's largest moons, harbors a global ocean beneath its icy crust. This vast body of liquid water, estimated to be up to 60 miles deep, could provide an ideal habitat for microbial life. The tidal forces exerted by Jupiter keep this ocean from freezing solid. potentially creating a stable environment over long periods. Similarly, Saturn's moon Enceladus boasts subsurface oceans and active geysers, hinting at the presence of hydrothermal vents similar to those found in Earth's deep oceans. These vents could supply the energy and nutrients necessary for life to thrive. Titan, another Saturnian moon, possesses a thick atmosphere and liquid methane lakes on its surface, presenting a unique chemical environment that could host exotic forms of life. The search for habitable worlds now extends beyond our solar system, with scientists considering the possibility of exomoons orbiting distant planets. These moons could offer stable environments in systems where planets might be too close or too far from their stars to support life directly. As our understanding of planetary systems grows, moons continue to play an increasingly important role in expanding our search for potentially habitable worlds. Studying the atmospheres of distant exoplanets is a remarkable feat of modern astronomy, achieved through ingenious methods and advanced technology. One primary technique is transit spectroscopy. When an exoplanet passes in front of its star, some of the starlight filters through the planet's atmosphere. By analyzing the spectrum of this light, scientists can identify the gases present in the exoplanet's atmosphere. Another method is direct imaging, which involves blocking out the bright light of the star to observe the much fainter planet. This technique allows astronomers to study the light reflected or emitted by the exoplanet itself, providing information about its atmospheric composition and temperature. High-resolution spectroscopy is also employed to detect specific molecules in exoplanet atmospheres. By measuring the Doppler shift of these molecular signatures as the planet orbits its star, scientists can confirm the presence of various compounds and even map their distribution across the planet's surface. These methods have led to fascinating discoveries, such as the detection of water vapor, methane, and even potential biosignatures on distant worlds. As our technology advances, we continue to refine these techniques, pushing the boundaries of our understanding of these alien atmospheres and inching closer to answering the profound question of whether we are alone in the universe. Super-Earths are a class of planets that have captured the imagination of astronomers and exoplanet hunters. These worlds are larger than Earth, but smaller than the ice giants like Neptune and Uranus in our solar system. Typically, super-Earths range from about 1.5 to 10 times the mass of our home planet. What makes super-Earths particularly intriguing is their potential to harbor life as we know it. Many of these planets orbit within the habitable zone of their stars, where temperatures could allow for liquid water on the surface. This characteristic alone makes them prime candidates in the search for extraterrestrial life. Moreover, super-Earths offer a unique opportunity to study planetary formation and evolution. Their size suggests they might have retained their primordial atmospheres, unlike smaller rocky planets that often lose their initial gas envelopes. This retention could provide valuable insights into the early stages of planetary development. Scientists are also keen to understand how super-Earths compare to our own planet in terms of geology, atmosphere, and potential habitability. As we continue to discover more of these worlds, each one adds another piece to the puzzle of planetary diversity in our galaxy, expanding our understanding of the cosmos and our place within it. Life forms on other planets could be radically different from those we know on Earth. While Earth life is carbon-based and requires water, alien organisms might use entirely different biochemistries. Some scientists speculate about the possibility of silicon-based life, which could thrive in extremely hot environments where carbon-based life would perish. The physical characteristics of extraterrestrial life could also be vastly different. Depending on the gravity, atmosphere, and light conditions of their home worlds, alien creatures might develop unique adaptations. On a planet with stronger gravity, life forms could be short and stocky. In low-gravity environments, they might grow tall and spindly. Sensory organs could also differ dramatically. Aliens might perceive wavelengths of light invisible to human eyes or detect magnetic fields as we sense sound. Their methods of communication could be unrecognizable to us, potentially using chemical signals, electrical impulses, or even gravity waves. Perhaps most intriguingly, alien life might not be confined to individual organisms as we understand them. Some scientists propose the possibility of planet-wide organisms or collective consciousnesses that function as a single entity. The sheer diversity of potential life forms in the universe is limited only by the laws of physics and chemistry, leaving room for forms of life beyond our current imagination. Establishing a colony on Mars presents numerous formidable challenges. The harsh Martian environment poses significant risks to human survival. The thin atmosphere offers little protection from cosmic radiation, exposing colonists to dangerous levels of harmful particles. The extreme cold, with temperatures often dropping well below freezing, necessitates robust heating systems and insulated habitats. Resource scarcity is another major hurdle. Mars lacks readily available water, oxygen, and food sources. Colonists would need to develop efficient methods to extract water from the Martian soil and atmosphere, produce oxygen through chemical processes, and grow food in controlled environments. These life support systems must be incredibly reliable, as any failure could quickly become catastrophic. The psychological impact of isolation cannot be overlooked. Martian colonists would be millions of kilometers from Earth, facing communication delays, and the knowledge that immediate return or rescue is impossible. This isolation, combined with confined living spaces and a lack of familiar comforts, could lead to severe mental health challenges. Logistical and technical issues also abound. Transporting the necessary equipment and supplies to Mars is extremely costly and complex. Maintaining and repairing critical systems in the harsh Martian environment would require extensive planning and redundancy. Despite these challenges, scientists and engineers continue to work on innovative solutions, bringing us closer to the possibility of human habitation on the Red Planet. Creating a sustainable ecosystem on another planet would be an immense challenge, requiring careful planning and advanced technology. The first step would involve selecting a planet with conditions that could potentially support life, such as Mars or a distant exoplanet with similar characteristics to Earth. Terraforming would be a crucial process, involving the modification of the planet's atmosphere, temperature, and surface to make it more Earth-like. This could include introducing greenhouse gases to warm the planet, generating a magnetic field to protect against harmful radiation, and creating bodies of water. Once the environment is suitable, we would need to introduce a carefully balanced selection of microorganisms, plants, and animals. These organisms would need to be chosen for their ability to thrive in the new environment and their roles in creating a functioning ecosystem. Algae and bacteria could be used to produce oxygen, while plants would help establish a sustainable carbon cycle. Maintaining this delicate balance would require constant monitoring and intervention. Advanced life support systems, recycling technologies, and sustainable energy sources would be essential to support human presence and manage the ecosystem. The goal would be to create a self-sustaining biosphere that could support human life indefinitely while minimizing our impact on the planet's newly established natural systems. For an off-world colony to thrive, several key resources would be essential. Water stands out as the most critical element, not only for human consumption but also for agriculture, oxygen production, and various industrial processes. A reliable source of water, whether from ice deposits or recycling systems, would be fundamental to the colony's survival. Energy would be another vital resource. Solar panels could harness the power of nearby stars, while nuclear reactors might provide a consistent energy supply, especially for colonies far from a star or on worlds with long periods of darkness. This energy would power life support systems, manufacturing facilities, and all the technology needed for daily life in an alien environment. Breathable air is equally crucial. While some planets or moons might have traces of oxygen, most off-world colonies would need to generate their own breathable atmosphere. This could be achieved through a combination of plant life in greenhouses and artificial air recycling systems that remove carbon dioxide and other contaminants while replenishing oxygen. Lastly, the ability to produce food would be essential for long-term survival. Hydroponic or aeroponic systems could allow for efficient crop growth in controlled environments, providing colonists with fresh produce. Protein sources might include lab-grown meat or insect farming, which require less space and resources than traditional livestock. These food production methods would need to be carefully managed to ensure a balanced diet for all inhabitants of the off-world colony. Humans venturing to other planets would face significant challenges, requiring substantial adaptations to survive and thrive in alien environments. On a low-gravity world like Mars, our bodies would undergo noticeable changes. Our muscles and bones would weaken due to reduced stress, potentially leading to a taller, more slender physique. Over generations, humans might evolve denser bones to compensate for the decreased gravity. In environments with higher levels of radiation, such as on Mars or in space stations, our bodies could develop more efficient DNA repair mechanisms. This adaptation would help protect against genetic damage caused by cosmic rays and solar radiation. Additionally, our skin might produce more melanin or develop other protective pigments to shield against harmful ultraviolet radiation. On planets with different atmospheric compositions, our respiratory systems would need to adapt. For instance, in a carbon dioxide-rich atmosphere like that of Mars, our lungs might become more efficient at extracting oxygen from the thin air. Our blood could also evolve to carry oxygen more effectively throughout our bodies. The human digestive system would likely change to process new types of food sources found on other planets. Our gut microbiome would adapt to break down unfamiliar nutrients, and our bodies might become more efficient at extracting and storing essential vitamins and minerals from limited food supplies. These adaptations would occur gradually over many generations, shaping future humans into a species well-suited for life beyond Earth. Space colonists embarking on long-term missions would encounter a range of psychological challenges, many of which we are only beginning to understand. Isolation from Earth and loved ones would be a primary concern, as colonists grapple with the vast distances separating them from familiar support networks. This physical and emotional separation could lead to feelings of loneliness, depression, and anxiety. The confined living spaces of space habitats would pose another significant challenge. Colonists would need to adapt to limited personal space and constant proximity to others, potentially leading to interpersonal conflicts and stress. The lack of privacy and the need for constant cooperation in a high-stakes environment could strain relationships and individual mental health. Adapting to the alien environment of space or another planet would also present unique psychological hurdles. The absence of familiar sensory inputs like Earth's day-night cycle, weather patterns, and natural landscapes could disorient colonists and disrupt their circadian rhythms. This sensory deprivation might lead to mood disturbances and cognitive difficulties over time. Lastly, the ever-present danger of the space environment would likely cause chronic stress. The knowledge that a small mistake or equipment failure could be fatal would weigh heavily on colonists' minds. Coping with this constant threat while maintaining focus on mission objectives would require exceptional mental resilience and well-designed support systems to ensure the long-term psychological well-being of space colonists. Protecting space colonies from cosmic radiation is a critical challenge for future space exploration and habitation. One effective approach involves using advanced shielding materials. Water, for example, is an excellent radiation absorber and could be stored in the walls of spacecraft or habitats. Polyethylene, a common plastic, is another promising material due to its high hydrogen content, which effectively blocks cosmic rays. Another strategy is to utilize the natural resources available on celestial bodies. On Mars, for instance, colonists could build habitats underground or use the planet's soil to create thick, protective walls. This would take advantage of the natural shielding provided by the Martian regolith. Magnetic fields offer another potential solution. By generating artificial magnetic fields around a space colony, we could deflect charged particles, mimicking Earth's natural magnetosphere. This technology is still in development, but shows promise for future applications. Lastly, advances in medicine and genetics could play a role in radiation protection. Researchers are exploring ways to enhance human cells' ability to repair radiation damage or even make our bodies more resistant to radiation effects. While these methods are still theoretical, They represent exciting possibilities for safeguarding future space explorers and colonists. Artificial intelligence could become a crucial component in the complex task of managing space colonies. As we venture beyond Earth, AI systems might oversee critical life support functions, monitoring and adjusting oxygen levels, temperature, and radiation shielding to ensure a safe environment for colonists. These intelligent systems could also optimize resource usage, managing water recycling, waste processing, and food production to maximize efficiency in the closed ecosystem of a space habitat. In the realm of decision-making, AI could analyze vast amounts of data to assist human leaders in making informed choices about colony operations, expansion plans, and potential hazards. This could include predicting maintenance needs, identifying potential structural weaknesses, or even forecasting space weather events that might impact the colony. Artificial intelligence might also play a significant role in the day-to-day lives of colonists. AI assistants could help schedule tasks, coordinate communal activities, and even provide personalized health recommendations based on each individual's physiological responses to the space environment. In emergencies, AI systems could rapidly assess situations, coordinate responses, and guide evacuation procedures if necessary. As space colonies grow and become more complex, artificial intelligence could serve as a vital tool in maintaining smooth operations, ensuring the safety and well-being of inhabitants, and adapting to the unique challenges of extraterrestrial living. However, the ultimate decisions and governance would likely remain in human hands, with AI serving as a powerful support system in this ambitious endeavor of space colonization. Establishing and maintaining communication between Earth and distant colonies presents significant challenges due to the vast distances involved. The primary method would likely rely on powerful radio transmitters and receivers using frequencies that can penetrate the atmosphere and travel through space with minimal interference. For colonies within our solar system, such as on Mars or the moons of Jupiter, we could use a network of relay satellites to boost signals and ensure continuous coverage. These satellites would orbit strategically to maintain line of sight between Earth and the colonies, even when celestial bodies obstruct direct transmission. For more distant colonies, perhaps in other star systems, we would need to develop advanced technologies to overcome the time delay caused by the speed of light. One possibility is quantum entanglement communication, which theoretically allows for instantaneous information transfer regardless of distance. However, this technology is still in its early stages and faces numerous practical hurdles. Another approach could involve sending powerful, focused laser beams carrying encoded data. This method would allow for higher data transfer rates than traditional radio waves, but would require extremely precise aiming and powerful telescopes to detect the faint signals across interstellar distances. Space colonization raises complex legal and ethical questions that humanity must grapple with as we venture beyond Earth. One key issue is the ownership and use of extraterrestrial resources. The Outer Space Treaty, signed by many nations, states that no country can claim sovereignty over celestial bodies. However, it remains unclear how this applies to private companies or individuals seeking to extract valuable materials from asteroids or other planets. Another consideration is the potential contamination of alien environments. Scientists worry about Earth microbes hitching a ride on our spacecraft and disrupting possible extraterrestrial ecosystems. Conversely, there are concerns about bringing unknown pathogens back to Earth. Strict planetary protection protocols aim to minimize these risks, but as missions become more frequent, maintaining sterility becomes increasingly challenging. The rights and governance of future space colonists also present thorny issues. What laws will apply in these new settlements? How will citizenship work for children born off Earth? These questions become even more complex when considering the vast distances and communication delays involved in interplanetary travel. Ethical debates also surround the very concept of colonizing other worlds. Some argue that humanity has a duty to expand and ensure our long-term survival, while others contend that we should focus on solving problems on Earth before spreading to other planets. As we move closer to making space colonization a reality, society will need to engage in serious discussions about these legal and ethical challenges. Space colonies would need to develop robust systems for resource production and recycling to achieve self-sufficiency. Initially, these outposts would rely heavily on supplies from Earth, but gradually, they would establish their own means of generating essentials like food, water, and oxygen. Hydroponic and aeroponic farming techniques would likely form the backbone of food production, allowing colonists to grow crops in controlled environments without soil. These methods use significantly less water and space than traditional agriculture, making them ideal for enclosed habitats. Alongside plant cultivation, lab-grown meat could provide protein sources without the need for large animal populations. Water and air recycling would be crucial for long-term sustainability. Advanced filtration and purification systems would need to operate with near-perfect efficiency, constantly cleaning and recirculating these vital resources. Oxygen could be generated through electrolysis of water or extracted from regolith on planets and moons with the right mineral composition. Energy production would be another key factor in self-sufficiency. Depending on the colony's location, solar panels, nuclear reactors, or other innovative power sources might be employed. As colonies expand, they could begin mining local resources for construction materials and other necessities, further reducing their reliance on Earth and paving the way for true independence in the cosmos. Space holds a treasure trove of valuable resources that could revolutionize our approach to manufacturing and technology. Asteroids, in particular, are prime targets for space mining operations. These celestial bodies often contain substantial deposits of precious metals such as gold, platinum, and palladium, which are rare on Earth but essential for many high-tech industries. Perhaps even more exciting is the presence of rare Earth elements in some asteroids. These elements, crucial for producing electronics and renewable energy technologies, are challenging to extract on Earth due to their scarcity and the environmental impact of mining operations. Space mining could provide a more sustainable source of these vital materials. Water ice, found on the Moon and some asteroids, is another invaluable resource. In space, water can be broken down into hydrogen and oxygen, providing fuel for spacecraft and life support systems for future space colonies. This could significantly reduce the cost and complexity of deep space exploration by allowing spacecraft to refuel at various points in the solar system. Helium-3, an isotope rarely found on Earth but present in the lunar regolith, has immense potential as a fuel for nuclear fusion reactors. If fusion technology becomes viable, helium-3 could become one of the most valuable resources in the solar system, potentially solving Earth's energy crisis and powering interplanetary travel. Asteroid mining represents a promising frontier in space exploration and resource acquisition. The process would likely begin with detailed surveys of near-Earth asteroids, using telescopes and space probes to identify the most mineral-rich candidates. Once a suitable asteroid is selected, robotic spacecraft would be dispatched to extract valuable materials such as platinum, gold, and rare earth elements. These robotic miners could employ various techniques depending on the asteroid's composition. For rocky asteroids, mechanical diggers might scrape and collect material from the surface. In the case of metallic asteroids, magnetic separators could be used to gather iron-rich particles. Some proposals even suggest using concentrated sunlight to heat the asteroid's surface, causing metals to vaporize for easy collection. Water extraction could be another key focus of asteroid mining operations. Many asteroids contain significant amounts of water ice, which could be melted and electrolyzed to produce hydrogen and oxygen. These elements are crucial for rocket fuel and life support systems, potentially enabling the establishment of refueling stations in space. The extracted resources would then need to be transported back to Earth or to space-based manufacturing facilities. This could involve using the mined materials to construct rudimentary spacecraft on site, or developing specialized cargo vessels designed for long-distance space hauling. As technology advances, asteroid mining could become a vital component of our space economy, providing resources for both terrestrial and extraterrestrial use. Space mining requires a suite of advanced technologies to overcome the challenges of operating in the harsh environment beyond Earth. Robust spacecraft capable of long-duration missions are essential, equipped with advanced propulsion systems to reach distant asteroids or other celestial bodies. These craft need to withstand extreme temperatures, radiation, and micrometeoroid impacts. Specialized mining equipment adapted for low-gravity environments is crucial. This includes drills, excavators, and processing units designed to function without the need for traditional mining practices that rely on Earth's gravity. Automated systems and artificial intelligence play a vital role, allowing for remote operation and decision-making when communication delays with Earth make real-time control impossible. Resource extraction and processing technologies are another critical component. These systems must be capable of identifying valuable materials, extracting them efficiently, and processing them into usable forms, all while minimizing waste and energy consumption. In situ resource utilization techniques are particularly important, allowing for the production of fuel, water, and other necessities directly from mined materials. Lastly, advanced life support systems are necessary to sustain human workers in space for extended periods. This includes reliable air and water recycling, radiation shielding, and medical facilities. As space mining operations expand, the development of permanent off-world habitats may become essential, requiring technologies for constructing and maintaining livable environments in the unforgiving vacuum of space. Space mining could revolutionize Earth's economy and resource management by providing access to vast quantities of valuable materials. Asteroids and other celestial bodies contain abundant resources such as platinum, gold, and rare Earth elements that are scarce on our planet. Extracting these materials from space could alleviate pressure on Earth's limited reserves and potentially reduce the environmental impact of terrestrial mining operations. The influx of space-derived resources could lead to significant shifts in global markets. The increased supply of rare metals might drive down prices, making advanced technologies more affordable and accessible. This could accelerate innovation in various sectors, from electronics to renewable energy. Additionally, the space mining industry itself would create new jobs and economic opportunities, both in space operations and supporting industries on Earth. However, the introduction of space resources could also disrupt existing markets and industries. Traditional mining companies might face competition, leading to potential job losses in some sectors. Governments and international bodies would need to establish new regulations and policies to manage the extraction and distribution of space-based resources fairly. The development of space mining capabilities could also drive advancements in sustainable resource management on Earth. Technologies created for efficient extraction and processing in space environments might find applications in improving terrestrial mining practices. Furthermore, the perspective gained from utilizing extraterrestrial resources could encourage a more global and long-term approach to managing Earth's finite resources. Processing raw materials in space presents unique challenges due to the extreme conditions and limitations of the environment. One major obstacle is the lack of gravity, which affects many industrial processes we take for granted on Earth. Without gravity, liquids behave differently, making it difficult to separate materials or control chemical reactions. The harsh vacuum of space also complicates matters. Many Earth-based manufacturing techniques rely on atmospheric pressure, which is absent in space. This absence can cause materials to behave unpredictably, outgas, or even sublimate directly from solid to gas. Additionally, the extreme temperature fluctuations in space can cause materials to expand and contract rapidly, potentially compromising the integrity of equipment and final products. Energy supply is another significant hurdle. On Earth, we have abundant access to power sources, but in space, energy must be carefully managed and conserved. Solar power is often used, but it can be inconsistent depending on location and orbital position. This limited energy availability constrains the types and scale of processing operations that can be conducted. Lastly, the logistics of transporting raw materials and equipment to space are complex and expensive. Every kilogram sent to orbit comes at a substantial cost, which means space-based processing must be highly efficient and produce valuable products to justify the expense. Despite these challenges, researchers and engineers continue to develop innovative solutions, recognizing that in situ resource utilization will be crucial for future space exploration and colonization efforts. Space mining could revolutionize our approach to space exploration by providing resources directly in space. Asteroids and other celestial bodies contain valuable materials such as platinum, gold, and rare earth elements. These resources could be extracted and used to manufacture spacecraft components, fuel, and other necessary items without the need to launch them from Earth. One of the most promising aspects of space mining is water extraction. Water found on asteroids or the Moon can be split into hydrogen and oxygen, which are crucial components of rocket fuel. This could allow for the creation of refueling stations in space, dramatically reducing the cost and complexity of deep space missions. Additionally, space mining could provide the raw materials needed for large-scale space construction projects. Imagine building space habitats or interplanetary vessels using metals and other resources harvested directly from asteroids. This would significantly reduce the amount of material we need to launch from Earth, making ambitious space projects more feasible. Furthermore, the development of space mining technologies could lead to advancements in robotics, artificial intelligence, and resource extraction methods. These innovations could then be applied to improve exploration techniques, allowing us to probe deeper into our solar system and beyond with more efficient and capable spacecraft. The legal framework for space resource exploitation is still evolving as humanity takes its first steps into this new frontier. Currently, the primary international agreement governing space activities is the Outer Space Treaty of 1967. This treaty establishes that space exploration should be carried out for the benefit of all humanity and that no nation can claim sovereignty over celestial bodies. However, the Outer Space Treaty does not explicitly address the issue of resource extraction from asteroids, moons, or planets. This ambiguity has led to ongoing debates and attempts to create more specific regulations. In recent years, some countries have passed national laws to encourage and regulate space mining activities. The United States, for example, enacted the Space Resource Exploration and Utilization Act in 2015, which grants companies the rights to resources they extract from space. These national laws have sparked international discussions about the need for a more comprehensive global framework. The United Nations Committee on the Peaceful Uses of Outer Space has been working on developing guidelines for the sustainable use of space resources. Their goal is to balance the interests of spacefaring nations and private companies with the principle that space exploration should benefit all of humanity. As more countries and private enterprises develop the capability to exploit space resources, the pressure to establish clear international regulations will likely increase. The challenge lies in creating a framework that encourages innovation and exploration while ensuring equitable access and preventing conflicts over extraterrestrial resources. Space mining operations could have significant impacts on the solar system's environment. As we venture beyond Earth to extract resources from asteroids, moons, and planets, we risk altering delicate cosmic ecosystems that have remained undisturbed for billions of years. One major concern is the potential disruption of orbital dynamics. Removing large amounts of mass from asteroids or moons could alter their trajectories, potentially leading to collisions or changes in the gravitational balance of planetary systems. This could have far-reaching consequences for the stability of the solar system over long periods. The extraction process itself poses risks. Mining activities could release dust and debris into space, creating clouds of particles that might interfere with spacecraft operations or obscure astronomical observations. Additionally, the use of explosives or other extraction methods could fragment smaller bodies, increasing the amount of space debris and potentially creating new hazards for future exploration. There are also concerns about contamination. Earth-based microorganisms carried on mining equipment could potentially survive in space and contaminate other celestial bodies, complicating the search for extraterrestrial life and potentially altering alien environments in ways we cannot predict. As we expand our presence in the solar system, careful consideration of these environmental impacts will be crucial to ensure sustainable and responsible space exploration. Robots and artificial intelligence are poised to revolutionize space mining operations, offering solutions to the challenges of extracting resources from distant celestial bodies. These advanced technologies can withstand the harsh conditions of space, including extreme temperatures, radiation, and low-gravity environments that would be hazardous or impossible for human workers. Robotic systems, guided by sophisticated artificial intelligence, could be deployed to survey potential mining sites on asteroids, moons, or planets. These machines would use an array of sensors and analytical tools to identify valuable minerals and map out the most efficient extraction methods. AI algorithms could process vast amounts of data in real time, making critical decisions about where to drill, how to navigate treacherous terrain, and how to adapt to unexpected obstacles. Once mining operations begin, robots would take on the physically demanding tasks of excavation, processing, and transportation of materials. These machines could work continuously without the need for rest, dramatically increasing productivity. Artificial intelligence would optimize these processes, ensuring maximum efficiency and minimal waste. It could also predict equipment failures and schedule maintenance, reducing downtime and extending the lifespan of mining operations. Furthermore, as space mining ventures expand, AI could manage complex logistics, coordinating fleets of robotic miners across multiple sites and orchestrating the delivery of extracted resources back to Earth or to space-based manufacturing facilities. This level of automation and intelligence would not only make space mining more feasible, but could also pave the way for sustainable off-world resource utilization, supporting future space exploration and colonization efforts. Space mining could revolutionize the construction of large-scale space structures by providing abundant resources directly in orbit or on celestial bodies. This approach would significantly reduce the cost and complexity of launching materials from Earth, which is currently a major limiting factor in space construction. Asteroids and other small bodies in our solar system are rich in valuable metals and minerals. These include iron, nickel, and platinum group metals, which are essential for building spacecraft, space stations, and other orbital structures. By extracting these materials in space, we could manufacture structural components, fuel tanks, and even entire habitats without the need for Earth-based launches. Water, another crucial resource found on many asteroids and moons, could be split into hydrogen and oxygen for use as rocket fuel. This would enable the creation of refueling stations throughout the solar system, greatly extending the range and capabilities of construction vessels and transport ships. Moreover, space mining could provide materials for advanced manufacturing techniques such as three-dimensional printing in microgravity. This would allow for the creation of large, complex structures that would be impossible to build on Earth or launch in one piece. As we expand our presence in space, the ability to source and process materials beyond Earth will become increasingly vital for sustainable space exploration and colonization. A Dyson sphere is a hypothetical megastructure that completely encompasses a star to capture most or all of its energy output. This concept, proposed by physicist Freeman Dyson in 1960, imagines a shell or swarm of orbiting satellites surrounding a star, harnessing its immense power for the use of an advanced civilization. Constructing a Dyson sphere would be an enormous undertaking, requiring technology far beyond our current capabilities. One approach might involve building a vast network of solar panels or collectors in orbit around a star. These would gradually expand to cover more and more of the star's surface area, capturing an increasing amount of its energy. Another method could be to dismantle planets and asteroids in a star system, using their raw materials to construct the sphere. This would provide the necessary resources for such a massive project. Advanced robotics and artificial intelligence would likely be crucial for managing the construction process. The engineering challenges are staggering. The structure would need to withstand the intense gravitational forces and radiation from the star while maintaining its position. It would also require a way to dissipate excess heat to prevent the sphere from melting. While currently beyond our reach, the concept of Dyson spheres continues to captivate scientists and science fiction enthusiasts alike, representing the ultimate in energy harvesting technology. Building and maintaining large-scale space stations presents numerous engineering challenges that push the boundaries of our technological capabilities. The process begins on Earth, where modular components are designed and constructed to withstand the rigors of space travel. These components must be lightweight yet durable, able to protect against radiation and micrometeorites while providing a habitable environment for astronauts. Launch vehicles, such as heavy-lift rockets, are crucial for transporting these modules into orbit. Once in space, the modules are carefully assembled using robotic arms and spacewalking astronauts. This assembly process requires precise coordination and can take months or even years to complete, depending on the size and complexity of the station. Maintaining a space station is an ongoing task that demands constant attention. Life support systems must be monitored and serviced regularly to ensure a steady supply of breathable air, clean water, and proper waste management. Power generation, typically through solar panels, requires periodic adjustments and repairs to maximize efficiency. Additionally, the station's orbit must be regularly boosted to counteract the effects of atmospheric drag, which gradually pulls the structure closer to Earth. As we look to the future, advanced technologies like in-space manufacturing and assembly could revolutionize space station construction. Three-dimensional printing in microgravity might allow for the creation of large structures directly in orbit, reducing the need for Earth-based manufacturing and complex assembly procedures. Developing more efficient recycling systems and exploring new power sources, such as nuclear propulsion, could also enhance our ability to build and sustain larger, more capable space stations for long-term human habitation and scientific research in the cosmos. O'Neill cylinders are massive space habitats designed to house human populations in orbit. Proposed by physicist Gerard O'Neill in the 1970s, these structures would be cylindrical in shape, measuring several kilometers in diameter and potentially tens of kilometers long. The cylinder would rotate to create artificial gravity along its inner surface, where people would live and work. These colossal habitats could support human life by replicating Earth-like conditions. The rotation would provide a gravitational force similar to Earth's, crucial for long-term human health. The inner surface would be divided into alternating strips of land and windows. The land areas would support agriculture and living spaces, while the windows would allow natural sunlight to enter, regulated by adjustable mirrors. Atmosphere, water, and other essential resources would be carefully managed within the closed system. Advanced life support systems would recycle air and water, while carefully controlled ecosystems would help maintain environmental balance. Energy would be abundant, sourced from the sun via large solar panels or mirrors, focusing sunlight into the cylinder. O'Neill cylinders could potentially house tens of thousands or even hundreds of thousands of people, offering a solution for long-term space habitation. They represent a bold vision of humanity's future in space, combining engineering ingenuity with the goal of creating sustainable, Earth-like environments beyond our home planet. Creating artificial gravity in space habitats is a crucial challenge for long-term space exploration and colonization. One of the most promising methods involves rotation. By spinning a cylindrical or wheel-shaped habitat, we can generate a centrifugal force that mimics gravity. The concept is similar to the feeling you experience on a spinning amusement park ride. As the habitat rotates, objects and people inside are pushed outward, creating a force that feels like gravity pulling them toward the outer wall. This wall effectively becomes the ground for the inhabitants. The amount of artificial gravity generated depends on the radius of the habitat and its rotational speed. Larger habitats can rotate more slowly to produce the same gravitational effect, which is preferable as it reduces motion sickness and other potential health issues associated with rapid rotation. Another approach being researched is the use of linear acceleration. This method involves constantly accelerating a spacecraft in one direction, then decelerating halfway through the journey. However, This requires enormous amounts of energy and is more suitable for interplanetary travel than stationary habitats. Inflatable structures offer exciting possibilities for future space habitats. These expandable modules can be launched in a compact form and then inflated once in orbit or on the surface of another world. This approach allows for much larger living spaces than traditional rigid modules, while still fitting within the payload constraints of launch vehicles. The key advantage of inflatable habitats is their ability to provide spacious interiors with minimal launch mass. Once deployed, these structures can offer astronauts roomy environments for long-duration missions, potentially improving both physical and psychological well-being. The flexible nature of the materials used also means they can be more resilient to impacts from micrometeoroids and space debris. Ongoing research and development are focusing on enhancing the durability and radiation shielding properties of inflatable habitats. Advanced materials and multi-layer designs aim to provide protection comparable to, or even superior to, traditional aluminum structures. Some concepts incorporate self-healing technologies to automatically seal small punctures, further increasing long-term reliability. As we look toward establishing permanent bases on the Moon or Mars, inflatable structures could play a crucial role. They might serve as greenhouses for growing food, large-scale living quarters, or even form the basis of entire settlements. Their versatility and efficiency make them a promising technology for expanding human presence beyond Earth. Protecting space habitats from cosmic radiation and debris is a critical challenge for long-term human presence beyond Earth. One effective approach involves using multiple layers of shielding materials. The outer layer could consist of tough, impact-resistant materials like advanced composites or metal alloys to deflect or break up incoming debris. Beneath this, a layer of hydrogen-rich materials, such as polyethylene or water, could help absorb and disperse cosmic radiation. Water is particularly useful, as it serves multiple purposes, acting as a radiation shield, a resource for the habitat, and potentially as a medium for growing food. Some designs propose surrounding the entire habitat with a water jacket several meters thick. Magnetic shielding, similar to Earth's magnetosphere, could also be employed to deflect charged particles. This would involve creating a magnetic field around the habitat using superconducting magnets. While energy-intensive, this method could significantly reduce the amount of physical shielding required. For added protection, habitats could be partially buried in the surface of a moon or asteroid, using the natural material as an additional barrier against radiation and impacts. This approach, combined with artificial shielding, could provide comprehensive protection for space dwellers while allowing for expansion and resource utilization. Recycling resources in a closed space environment presents unique and complex challenges. In the confined quarters of a spacecraft or space station, every gram of material becomes precious, and waste is a luxury astronauts cannot afford. The primary hurdle is creating a completely closed-loop system where all resources are continuously reused and recycled with minimal loss. Water recycling is a critical concern in space. While current systems can reclaim a high percentage of water from urine, sweat, and even humidity in the air, achieving 100% efficiency remains elusive. Trace contaminants build up over time, requiring periodic resupply of fresh water or advanced filtration systems that are energy-intensive and prone to mechanical failure. Air recycling poses another significant challenge. Carbon dioxide must be constantly removed and converted back into breathable oxygen. Current systems use chemical processes or algae-based bioreactors, but these methods are not perfect and require regular maintenance. Additionally, other trace gases that accumulate in the closed environment need to be filtered out to prevent potential health hazards. Solid waste recycling is perhaps the most daunting task. Food packaging, used equipment, and human waste all need to be processed and repurposed. While composting systems for organic waste show promise, recycling plastics and metals in the microgravity environment of space requires innovative solutions that are still in development. The ultimate goal is to create a system where every particle of matter serves a purpose, with nothing going to waste in the unforgiving vacuum of space. Growing food in space habitats presents unique challenges, but innovative solutions are being developed to ensure sustainable nutrition for future space explorers. One promising approach is hydroponic farming, which uses nutrient-rich water instead of soil to grow plants. This method is particularly well suited to the controlled environments of space habitats, as it conserves water and allows for precise nutrient delivery. Vertical farming techniques can maximize the use of limited space in these habitats. By stacking plants in layers, we can grow more food in a smaller area. This approach is complemented by the use of LED lighting, which can be tailored to provide optimal wavelengths for plant growth without the need for natural sunlight. Aeroponics is another cutting-edge method being explored for space agriculture. In this system, plant roots are suspended in air and misted with a nutrient solution. This technique uses even less water than hydroponics and allows for better oxygenation of the roots, potentially leading to faster growth and higher yields. Researchers are also investigating the potential of growing microgreens and other nutrient-dense crops that can provide maximum nutritional value in minimal space. These strategies, combined with careful selection of plant varieties suited to the unique conditions of space habitats, could pave the way for efficient and sustainable food production beyond Earth. Designing long-term space habitats requires careful attention to psychological factors that can significantly impact astronaut well-being and mission success. One crucial consideration is providing adequate personal space and privacy. In the confined environment of a space habitat, astronauts need areas where they can retreat and have moments of solitude to maintain mental balance. Another important aspect is creating a sense of normalcy and familiarity. Incorporating elements that remind astronauts of Earth, such as plants, natural light cycles, and communal areas for social interaction, can help alleviate feelings of isolation and homesickness. Additionally, designers must consider the need for variety and stimulation. Monotony can lead to boredom and decreased cognitive function, so habitats should include spaces for exercise, entertainment, and creative activities. The psychological effects of long-term exposure to artificial environments must also be addressed. This includes managing the potential for sensory deprivation and ensuring that the habitat provides adequate sensory input through varied textures, colors, and sounds. Furthermore, the design should facilitate clear day-night cycles to maintain circadian rhythms, which are crucial for mental and physical health. Lastly, the habitat must support effective communication with Earth and provide opportunities for astronauts to maintain connections with family and friends. This social support is vital for maintaining morale and psychological well-being during extended periods in space. By carefully considering these psychological factors, designers can create space habitats that not only keep astronauts physically safe, but also support their mental health and overall mission performance. Space habitats face unique challenges when it comes to long-term power generation. One promising solution is the use of advanced solar arrays. These high-efficiency panels could capture energy from distant stars, converting it into electricity to sustain life support systems and other critical functions. As technology improves, these arrays are becoming more compact and resilient, able to withstand the harsh conditions of space for extended periods. Nuclear power presents another viable option for space habitats. Small, safe nuclear reactors could provide a consistent energy source for decades without refueling. These reactors would be designed with multiple safety features to prevent accidents and contain any potential radiation. The long-lasting nature of nuclear fuel makes it particularly suitable for deep space missions or habitats far from the Sun. For habitats closer to planets or moons, geothermal energy could be harnessed. By tapping into the heat generated by planetary cores, a steady stream of power could be produced. This method would be especially effective on worlds with high volcanic activity, such as Jupiter's moon Io. Fusion power, while still in development, holds immense potential for future space habitats. If successfully harnessed, fusion could provide an almost limitless supply of clean energy, using readily available hydrogen as fuel. This would allow space colonies to become truly self-sufficient, generating all the power they need for centuries without resupply from Earth. We communicate with our most distant spacecraft through an ingenious network of massive radio antennas spread across Earth. This system, known as the Deep Space Network, consists of 3 complexes strategically positioned around the globe in California, Spain, and Australia. These locations ensure continuous coverage as our planet rotates, allowing uninterrupted contact with far-flung explorers like Voyager 1 and Voyager 2. The process of communicating across such vast distances is no small feat. Radio waves, traveling at the speed of light, can take hours to reach these distant spacecraft. For example, a signal sent to Voyager 1, currently over 14 billion miles from Earth, takes about 21 hours to arrive. The return message takes another 21 hours, resulting in a round-trip communication time of nearly 2 days. To overcome the extreme distances involved, the Deep Space Network uses powerful transmitters and incredibly sensitive receivers. These can detect signals as faint as 1/billionth of 1/trillionth of a watt, about 20 billion times weaker than the power required for a digital watch. This remarkable sensitivity allows us to maintain contact with spacecraft, exploring the outer reaches of our solar system and beyond. As we continue to push the boundaries of space exploration, engineers are developing new technologies to enhance our long-distance communication capabilities. These include optical communication using lasers, which could dramatically increase data transmission rates, allowing future missions to send back more detailed information from the far corners of our cosmic neighborhood. Communicating across the immense distances of space presents numerous challenges for scientists and engineers. The primary obstacle is the sheer scale of the cosmos. Even at the speed of light, radio signals can take hours, days, or even years to reach their destination, depending on how far they need to travel. For example, sending a message to a spacecraft orbiting Mars takes between 3 and 22 minutes, depending on the planet's positions. This delay makes real-time communication impossible and complicates mission control for robotic explorers and potential future human missions. Signal strength is another significant hurdle. As radio waves travel through space, they spread out and weaken. By the time they reach their distant target, the signal can be incredibly faint, requiring large, powerful antennas to detect and interpret the message. This issue becomes more pronounced the farther we attempt to communicate. Space itself poses additional challenges. Interference from cosmic radiation, solar activity, and other celestial phenomena can distort or disrupt signals. Scientists must develop sophisticated error correction techniques and redundant systems to ensure messages are received accurately, especially for critical communications with distant spacecraft exploring our solar system and beyond. Establishing communication with extraterrestrial civilizations is a complex challenge that has intrigued scientists for decades. One of the primary methods we currently employ is the use of powerful radio telescopes to send and receive signals across vast distances of space. These telescopes can transmit carefully crafted messages containing information about Earth and humanity, while also scanning the cosmos for any signs of artificial signals that might indicate intelligent life. Another approach involves the use of optical communication, utilizing powerful lasers to send encoded messages through space. This method could potentially allow for faster and more precise communication over interstellar distances. Scientists are also exploring the possibility of using neutrinos or gravitational waves as alternative means of communication, as these particles can travel through space relatively unimpeded. Some researchers propose sending physical artifacts, such as time capsules or probes, into space with information about our civilization. The Voyager Golden Records, launched aboard the Voyager spacecraft in 1977, are an example of this approach. These records contain sounds, images, and information about Earth, serving as a cosmic message in a bottle. Developing a universal language or mathematical code that could be understood by other intelligent species is another crucial aspect of extraterrestrial communication. Scientists are working on creating messages based on fundamental scientific principles and mathematical concepts that might be recognizable to advanced civilizations, regardless of their biological or cultural differences from humans. The speed of light delay is the time it takes for electromagnetic signals, including radio waves, to travel between 2 points in space. Light and radio waves move at the speed of light, which is approximately 300,000 kilometers per second in a vacuum. While this seems incredibly fast, the vast distances in space mean that even at this speed, signals can take significant time to reach their destination. This delay profoundly impacts space communication, especially for missions to distant planets or deep space probes. For example, radio signals between Earth and Mars can take anywhere from 3 to 22 minutes to make a one-way trip, depending on the planet's positions in their orbits. This means that a simple question and answer exchange could take up to 44 minutes. The speed of light delay creates unique challenges for space exploration. It makes real-time control of spacecraft or rovers on other planets impossible. Instead, mission controllers must send a set of instructions and then wait to see the results. This delay also affects how we receive data and images from space missions, as the information we get is always slightly outdated by the time it reaches us. For future human missions to Mars or beyond, the speed of light delay will be a significant hurdle. Astronauts will need to be more autonomous, as they cannot rely on immediate support or instructions from Earth. This delay also emphasizes the need for robust onboard systems and decision-making capabilities in our spacecraft and rovers, as they must operate independently for extended periods. Quantum entanglement could transform space communication by enabling instantaneous data transfer across vast cosmic distances. This phenomenon, often described as spooky action at a distance, involves particles that remain connected regardless of their separation. When one entangled particle is measured, the state of its partner is immediately known, no matter how far apart they are. This property could allow for the creation of quantum communication networks that span the solar system or even reach distant stars. Unlike traditional radio signals that weaken over long distances and experience time delays, quantum entanglement could provide instant, secure communication free from these limitations. Spacecraft exploring the outer reaches of our solar system could maintain real-time contact with Earth, dramatically improving our ability to conduct deep space missions. Moreover, quantum communication would be inherently secure, as any attempt to intercept the information would disrupt the entanglement and be immediately detectable. While significant technical challenges remain, the potential of quantum entanglement to revolutionize space communication is immense. It could usher in a new era of space exploration, allowing humanity to extend its reach further into the cosmos while maintaining instant connections across the vastness of space. Radio waves are a crucial tool in our quest to find signs of extraterrestrial intelligence. These electromagnetic waves can travel vast distances across space with minimal interference, making them ideal for interstellar communication. Scientists use massive radio telescopes to scan the cosmos, listening for any unusual signals that might indicate artificial origin. The search for extraterrestrial intelligence, often called SETI, focuses on specific radio frequencies. One key area of interest is the so-called waterhole, a quiet band of the radio spectrum between the emission lines of hydrogen and hydroxyl. Many scientists believe this could be a logical channel for alien civilizations to use for communication, as it stands out from the cosmic background noise. Radio waves also allow us to study distant stars and planets, helping us identify potentially habitable worlds. By analyzing the radio emissions from these celestial bodies, we can gather information about their composition, temperature, and even atmospheric conditions. This knowledge guides our search for extraterrestrial life, helping us focus on the most promising targets. While we have yet to detect any confirmed signals from alien civilizations, the use of radio waves in SETI has already yielded valuable scientific discoveries. It has enhanced our understanding of the universe and pushed the boundaries of our technology, driving innovations in radio astronomy and signal processing that benefit many fields beyond the search for extraterrestrial intelligence. Decoding messages from an alien civilization would be an immense challenge, requiring a multidisciplinary approach combining linguistics, mathematics, computer science, and astrophysics. The first step would likely involve identifying patterns within the received signal, as any intelligent communication would contain recognizable structure. Scientists might look for mathematical constants or prime numbers, which could serve as a universal language. These fundamental concepts might be used by aliens to establish initial contact and provide a basis for further communication. Advanced computer algorithms would be crucial in analyzing vast amounts of data to detect these patterns. Once a basic understanding is established, researchers could attempt to decipher more complex information. This might involve creating a kind of alien Rosetta Stone, linking known concepts to unknown symbols or signals. Comparative analysis with human languages and communication systems could provide insights into the alien message structure. The process would likely be iterative and time-consuming, involving trial and error and constant refinement of decoding techniques. Success would depend on the complexity of the message, the similarities between alien and human thought processes, and our ability to think beyond our own cultural and biological constraints. The potential rewards, however, would be immeasurable, offering unprecedented insights into extraterrestrial life and potentially revolutionizing our understanding of the universe. As we explore the possibilities of communicating across the vast distances of space, scientists have considered several intriguing alternatives to traditional radio waves. One promising option is the use of laser beams to transmit data. These focused beams of light could potentially carry more information and travel farther than radio waves without dispersing as much. Another fascinating proposal involves neutrino-based communication. Neutrinos are subatomic particles that rarely interact with matter, allowing them to pass through solid objects with ease. This property could make them ideal for sending messages through dense celestial bodies or across great cosmic distances. Some researchers have even suggested harnessing gravitational waves for interstellar communication. These ripples in spacetime, first detected in 2015, could potentially carry information across the universe with minimal interference. However, the technology to generate and detect specific gravitational wave patterns for communication purposes is still purely theoretical. Quantum entanglement has also been proposed as a potential method for faster-than-light communication, though current understanding of physics suggests this may not be possible. Nevertheless, quantum technologies could play a role in enhancing the security and efficiency of other communication methods across interstellar distances. Maintaining reliable communication networks between distant space colonies presents significant challenges, but several promising technologies and strategies could help overcome the vast distances involved. Laser-based communication systems offer one potential solution, using tightly focused beams of light to transmit data across interplanetary or even interstellar distances. These systems can achieve much higher data rates than traditional radio communications and are less susceptible to interference. Another approach involves establishing a network of relay stations throughout the solar system. These stations would act as intermediaries, receiving and retransmitting signals between colonies, effectively extending the range of our communication capabilities. Such a network could potentially utilize asteroids or small moons as natural platforms for these relay stations. Quantum entanglement might also play a role in future space communication networks. While still largely theoretical, quantum communication could potentially allow for instantaneous data transfer across any distance, overcoming the time delays inherent in other forms of long-distance space communication. However, significant technological advancements would be required to make this a practical reality. Regardless of the specific technologies employed, redundancy and error correction will be crucial components of any intercolonial communication network. Multiple communication pathways and advanced data encoding techniques will help ensure that messages can be transmitted reliably even in the face of solar interference, equipment failures, or other disruptions. Communicating with alien life forms presents a complex web of ethical challenges that humanity must carefully navigate. One primary concern is the potential for cultural misunderstandings or unintended harm. Our attempts at communication could be misinterpreted as hostile or threatening, potentially sparking interstellar conflict. Conversely, we might inadvertently cause harm to an alien civilization by introducing concepts or technologies they are not prepared to handle. Another crucial ethical consideration is the question of representation. Who has the right to speak on behalf of Earth? The decision-making process for interstellar communication must be inclusive and consider diverse perspectives from across our planet. This raises issues of global governance and cooperation on an unprecedented scale. The impact of contact on both human and alien societies must also be carefully weighed. The revelation of extraterrestrial intelligence could profoundly affect human religions, cultures, and worldviews. Similarly, our messages could disrupt the natural development of an alien civilization. We must consider whether we have the right to potentially alter the course of another species' evolution or cultural progression. Lastly, there are concerns about information sharing and intellectual property rights. How much of our knowledge and culture should we freely offer to an alien civilization? Conversely, how would we handle receiving advanced alien knowledge or technology? These questions touch on issues of fairness, exploitation, and the potential for rapid, destabilizing changes to our own society. As we reach out to the stars, these ethical dilemmas demand our utmost attention and careful consideration. The Fermi paradox is a thought-provoking concept that addresses the apparent contradiction between the high probability of extraterrestrial civilizations existing in our vast universe and the lack of evidence for, or contact with, such civilizations. Named after physicist Enrico Fermi, this paradox emerged from a simple question: where is everybody? Given the enormous number of stars and planets in our galaxy, and the age of the universe, it seems logical that intelligent life should have emerged and spread throughout the cosmos by now. Yet, we have not detected any signs of alien civilizations. This absence of evidence is particularly puzzling when we consider our own technological progress and our increasing ability to search for signs of life beyond Earth. The significance of the Fermi paradox lies in its implications for our understanding of life in the universe and our place within it. It challenges our assumptions about the prevalence of life and intelligence and forces us to consider various explanations for the silence we observe. These explanations range from the possibility that intelligent life is extremely rare, to the idea that advanced civilizations destroy themselves before achieving interstellar travel, or even that they choose to remain hidden from us. The Fermi paradox also drives scientific inquiry and technological development in the search for extraterrestrial intelligence. It motivates us to improve our methods of detection, expand our search parameters, and critically examine our assumptions about how alien civilizations might communicate or make their presence known. The Fermi paradox serves as a cosmic mystery that continues to fuel our exploration of the universe and our quest to understand our place within it. The absence of confirmed alien contact has puzzled scientists and the public alike for decades. Several explanations have been proposed to account for this cosmic silence. One possibility is the vastness of space itself. The distances between stars are so immense that even if alien civilizations exist, their signals or probes might not have reached us yet. Another explanation is the potential rarity of life in the universe. While we know life emerged on Earth, the conditions necessary for complex life to evolve might be exceedingly uncommon. This idea, known as the rare Earth hypothesis, suggests that the confluence of factors required for intelligent life to develop could be exceptionally unusual. Technological limitations could also play a role. Our ability to detect and interpret potential alien signals is still in its infancy. It is possible that advanced civilizations use communication methods we have not yet discovered or cannot detect with our current technology. Additionally, the window of time during which a civilization is capable of and interested in interstellar communication might be relatively brief, further reducing the chances of contact. Lastly, some researchers propose the existence of a great filter, a hypothetical barrier that prevents civilizations from reaching a level of technological advancement necessary for interstellar communication or travel. This filter could be a catastrophic event or a developmental stage that most civilizations fail to surpass, explaining why we have not encountered evidence of alien life despite the vast number of potentially habitable planets in the universe. The Drake equation serves as a thought-provoking framework in our quest to understand the potential for extraterrestrial life in the universe. Developed by astronomer Frank Drake in 1961, this equation attempts to estimate the number of civilizations in our galaxy capable of communicating across interstellar distances. By breaking down the factors that could influence the existence and detectability of alien life, the Drake equation encourages scientists to consider various aspects of cosmic evolution and planetary development. These factors include the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, and the likelihood of life emerging and evolving into intelligent beings capable of interstellar communication. While the Drake equation does not provide a definitive answer, it guides our search for extraterrestrial intelligence by highlighting key areas of research. It prompts us to investigate exoplanets, study the conditions necessary for life, and develop advanced detection methods for potential alien signals. The equation also helps scientists prioritize targets for observation and allocate resources in the search for extraterrestrial life. Ultimately, the Drake equation reminds us of the vast possibilities that exist in our galaxy and beyond. It fuels our curiosity and drives us to explore the cosmos, always searching for signs that we are not alone in the universe. Our search for alien civilizations employs a variety of cutting-edge techniques and technologies. One primary method is the use of powerful radio telescopes to scan the cosmos for artificial signals that could indicate intelligent life. These massive instruments, like the Allen Telescope Array in California, listen for narrow-band radio emissions that are unlikely to occur naturally. Optical telescopes also play a crucial role, searching for signs of megastructures or other large-scale engineering projects that advanced civilizations might construct. Scientists look for unusual light patterns or infrared signatures that could suggest the presence of alien technology. Exoplanet research has opened up new avenues for the search. By studying the atmospheres of distant planets, we can look for chemical signatures that might indicate the presence of life or even industrial pollution from a technological civilization. The James Webb Space Telescope, with its unprecedented sensitivity, is expected to greatly enhance our ability to conduct these atmospheric studies. Some researchers are also exploring the possibility of detecting interstellar probes or artifacts within our own solar system. This includes analyzing unusual asteroid trajectories and scanning for artificial objects in stable orbits. While no conclusive evidence has been found, these diverse approaches demonstrate the scientific community's commitment to answering one of humanity's most profound questions. Are we alone in the universe? Advanced alien civilizations could be employing various sophisticated methods to conceal their existence from us. One intriguing possibility is the use of Dyson spheres or swarms, vast structures that completely encompass a star to harness its energy. These megastructures would not only provide enormous power to the civilization, but also effectively hide the star's light, making it appear dim or even invisible to our telescopes. Another potential concealment technique could involve manipulating the electromagnetic spectrum. Aliens might have developed technology to absorb or redirect all forms of radiation they emit, essentially creating a cosmic cloaking device. This would make their planets, spacecraft, and activities undetectable to our current observation methods. Some scientists speculate that advanced civilizations might exist in dimensions or states of matter we cannot yet perceive or understand. They could be utilizing exotic physics beyond our current knowledge, allowing them to exist alongside us without our awareness. This concept challenges our understanding of reality and the nature of intelligent life. Lastly, these civilizations might be deliberately avoiding contact, adhering to a policy of non-interference with less advanced species like ourselves. They could be observing us from afar, using technologies that mimic natural phenomena or cosmic background noise, ensuring their presence remains hidden until they deem us ready for contact. The Great Filter Theory is a concept that attempts to explain why we haven't encountered any signs of advanced alien civilizations despite the vast number of potentially habitable planets in our galaxy. This theory suggests that there are significant obstacles or challenges that civilizations must overcome to reach an advanced stage of development capable of interstellar travel and communication. These obstacles could occur at various points in a civilization's evolution, from the emergence of life to the development of complex organisms, intelligence, technology, and ultimately the ability to colonize other worlds. The Great Filter could be a single, nearly insurmountable hurdle or a series of challenging steps that most civilizations fail to overcome. In relation to space exploration, the Great Filter Theory has profound implications. If the filter lies in our past, it means humanity has already overcome significant challenges and might be one of the few civilizations to have done so. This scenario would suggest that we might be alone, or among very few advanced civilizations in the galaxy, making our efforts to explore and colonize space all the more important for the continuation of intelligent life. However, if the Great Filter lies in our future, it presents a sobering possibility. It could mean that there are still major challenges ahead that might prevent us from becoming an interstellar civilization. These challenges could range from self-destruction through warfare or environmental collapse to unforeseen cosmic events. Understanding and overcoming these potential future filters becomes crucial for the long-term survival and expansion of humanity into space. The discovery of microbial life within our solar system would revolutionize our understanding of life in the universe. Such a finding would provide concrete evidence that life can arise in environments beyond Earth, dramatically expanding the potential for life elsewhere in the cosmos. If we were to find microbes on Mars, Europa, or Enceladus, it would suggest that life might be more common than we currently believe. This discovery would force us to re-evaluate our definitions of habitable environments and the conditions necessary for life to emerge. It could indicate that life is a natural consequence of certain chemical and environmental conditions rather than a rare accident. Furthermore, studying these extraterrestrial microbes could offer insights into the origins of life on Earth. By comparing their biochemistry and genetic makeup to terrestrial life, we might uncover clues about the fundamental processes that lead to the emergence of living organisms. This knowledge could help us better understand how life began on our planet and potentially how it could arise elsewhere. The implications of such a discovery extend beyond our solar system. If life can develop independently in multiple locations within our cosmic neighborhood, it increases the likelihood of life existing in other star systems throughout the galaxy and the universe. This would profoundly impact our search for extraterrestrial intelligence and our understanding of our place in the cosmos. Dyson swarms are hypothetical megastructures consisting of numerous satellites or habitats orbiting a star to capture and utilize its energy. Named after physicist Freeman Dyson, these swarms represent a potential solution for advanced civilizations to meet their ever-growing energy needs. Unlike a solid Dyson sphere, which would completely enclose a star, a Dyson swarm allows for a more flexible and achievable approach to harnessing stellar energy. The individual components of the swarm could be solar panels, space habitats, or other energy-collecting devices, all working together to maximize energy capture from the host star. The presence of a Dyson swarm might be detectable to distant observers through several means. The swarm would likely cause unusual fluctuations in the star's light as the orbiting structures pass in front of it. Additionally, the infrared signature of the star system would be altered as the swarm absorbs and re-emits energy. Astronomers searching for signs of extraterrestrial intelligence consider Dyson swarms a potential technosignature of an advanced civilization. The ability to construct such a vast network of structures around a star would indicate a level of technological prowess far beyond our current capabilities, making Dyson swarms an intriguing subject in the search for cosmic neighbors. Distinguishing between natural phenomena and potential alien signals is a complex task that requires careful analysis and multiple lines of evidence. Scientists use a combination of advanced technologies and rigorous methodologies to investigate unusual signals from space. One key approach is to look for patterns that are unlikely to occur naturally. Natural phenomena often produce random or predictable signals, while an artificial signal might contain mathematical sequences or repeat in a specific way. Researchers also examine the frequency and duration of signals, as natural sources typically emit across a broad spectrum, while artificial transmissions might be narrowband or pulsed. Another important factor is the signal's origin. If a signal appears to come from a specific star system, especially one known to have potentially habitable planets, it becomes more intriguing. However, scientists must rule out terrestrial sources of interference, such as satellites or Earth-based transmitters, which can sometimes mimic extraterrestrial signals. Ultimately, confirming an alien signal would require multiple detections from different observatories and extensive peer review. Scientists remain cautious and skeptical, always seeking natural explanations first, before considering the possibility of extraterrestrial intelligence. This approach ensures that any extraordinary claims are backed by extraordinary evidence. Contact with an alien civilization would profoundly reshape human society in ways we can scarcely imagine. The confirmation that we are not alone in the universe would trigger a paradigm shift in our collective worldview, challenging our understanding of our place in the cosmos. The immediate effects would likely include a surge in scientific research and technological development as we strive to understand and communicate with the alien civilization. This could lead to rapid advancements in fields such as physics, biology, and astronomy, potentially revolutionizing our understanding of the universe and our own origins. Socially and culturally, the impact would be equally transformative. Religious beliefs, philosophical frameworks, and cultural identities would face unprecedented challenges, potentially leading to societal upheaval as we grapple with new realities. The nature of the alien civilization, whether peaceful or hostile, technologically superior or comparable to our own, would significantly influence these changes. Politically, contact might foster greater global unity as humanity faces a common experience, or it could exacerbate existing tensions as nations vie for access to alien knowledge and technology. The economic implications would be vast, with new industries emerging and existing ones being reshaped by alien concepts and technologies. Ultimately, contact with an alien civilization would mark a turning point in human history, fundamentally altering our perception of ourselves and our role in the universe. Prolonged exposure to microgravity has profound effects on the human body, altering its functions in ways that can be both fascinating and concerning. In the absence of Earth's gravitational pull, astronauts experience significant changes to their physiology, starting with a redistribution of bodily fluids. Without gravity to pull fluids downward, they shift upward, causing a puffy face and congestion in the upper body. This fluid shift leads to decreased blood volume and a weakening of the heart muscle, as it no longer needs to work as hard to pump blood against gravity. Bone density also decreases at an alarming rate, with astronauts losing up to 2% of their bone mass per month in space. Muscles, particularly those used for posture and movement on Earth, begin to atrophy without the constant challenge of gravity. The spine elongates in microgravity, causing astronauts to grow taller by up to 3 inches, often accompanied by back pain. Vision can be affected too, with some astronauts experiencing optic disc edema, a swelling of the optic nerve that can lead to vision problems. The immune system becomes less effective, potentially leaving astronauts more susceptible to illness. Perhaps most concerningly, exposure to cosmic radiation in space increases the risk of cancer and other health issues. Upon returning to Earth, astronauts face a challenging readjustment period as their bodies reacclimate to gravity, often experiencing dizziness, weakness, and difficulty with balance and coordination. These effects of microgravity highlight the ongoing challenges in preparing humans for long-duration space missions and potential colonization of other planets. Long-term space travel poses several significant health risks to astronauts. One of the primary concerns is the effects of microgravity on the human body. In the absence of Earth's gravity, astronauts experience bone loss and muscle atrophy, which can lead to increased risk of fractures and reduced physical strength upon return to Earth. Exposure to cosmic radiation is another major health hazard. Beyond the protective shield of Earth's atmosphere and magnetic field, astronauts are subjected to high-energy particles that can damage DNA and increase the risk of cancer and other radiation-related illnesses. The isolation and confinement of space travel can also take a toll on mental health. Astronauts may experience psychological stress, sleep disturbances, and cognitive changes due to the unique environment and separation from Earth. Lastly, the altered fluid distribution in microgravity can affect various bodily systems. This can lead to vision problems, weakened immune function, and cardiovascular deconditioning. Addressing these health risks is crucial for the success of long-duration space missions and the well-being of astronauts. Cosmic radiation poses a significant challenge for long-duration space missions, particularly those venturing beyond Earth's protective magnetic field. To safeguard astronauts from this invisible threat, scientists and engineers are developing several promising strategies. One approach involves creating advanced shielding materials for spacecraft and habitats. These materials, such as hydrogenated boron nitride nanotubes, can absorb or deflect harmful cosmic rays more effectively than traditional aluminum shields. Some researchers are even exploring the use of superconducting magnets to create a protective magnetic field around spacecraft, mimicking Earth's natural defense mechanism. Another mitigation strategy focuses on the human body itself. Scientists are investigating pharmaceuticals that could help repair cellular damage caused by radiation exposure. Additionally, dietary supplements rich in antioxidants might boost the body's natural defense mechanisms against radiation-induced harm. Careful mission planning also plays a crucial role in radiation protection. By timing deep space missions to coincide with periods of lower solar activity, we can reduce exposure to solar radiation. Furthermore, designing spacecraft with dedicated radiation shelters allows astronauts to seek additional protection during solar storms or when passing through high radiation areas like the Van Allen belts. Astronauts on extended missions confront a unique set of psychological challenges that test their mental resilience and emotional stability. One of the most significant issues is isolation, as crew members are physically separated from their families, friends, and the familiar comforts of Earth for months or even years at a time. This separation can lead to feelings of loneliness and homesickness, which may intensify as the mission progresses. The confined living space of a spacecraft or space station also presents challenges. Astronauts must adapt to limited privacy and personal space, which can cause stress and interpersonal conflicts among crew members. The constant proximity to the same individuals for extended periods can strain relationships and require exceptional teamwork and communication skills to maintain harmony. Another psychological hurdle is the monotony of daily routines in space. Despite the extraordinary nature of their work, astronauts often face repetitive tasks and limited recreational options, which can lead to boredom and a decrease in motivation over time. This lack of variety can affect cognitive function and overall well-being, requiring astronauts to develop strategies to stay mentally engaged and productive. The ever-present risk of danger in the harsh space environment adds another layer of psychological stress. Astronauts must remain vigilant and prepared for potential emergencies while managing the underlying anxiety that comes with living in such a precarious situation. This constant state of alertness, combined with the physical effects of microgravity on the body, can disrupt sleep patterns and contribute to fatigue, further challenging an astronaut's mental state during long-duration missions. Space travel poses unique challenges to human reproduction and fetal development due to the extreme environment of space. Microgravity and increased radiation exposure are two key factors that can significantly affect these processes. In microgravity, the human body undergoes various physiological changes. These alterations could potentially impact reproductive functions. For instance, Studies have shown that microgravity can affect hormone levels, which play a crucial role in both male and female reproductive systems. This hormonal imbalance might lead to difficulties in conception or maintaining a pregnancy. Radiation exposure in space is another major concern. Beyond Earth's protective magnetosphere, astronauts are exposed to higher levels of cosmic radiation. This increased radiation can damage DNA, potentially leading to mutations in reproductive cells or developing fetuses. Such genetic alterations could result in developmental abnormalities or increase the risk of cancer in offspring. Furthermore, the physical stresses of space travel, including launch and re-entry, could pose risks to a developing fetus. The extreme forces experienced during these phases might lead to complications or premature birth. While research in this area is ongoing, these potential risks highlight the need for careful consideration and further study before long-term space missions or space colonization can become a reality for humans. Living in space presents unique challenges that could drive significant adaptations in human physiology over multiple generations. One of the most noticeable changes would likely occur in our skeletal structure. Without the constant pull of gravity, bones would become less dense and potentially more fragile. Future space-dwelling humans might evolve to have longer, thinner limbs and more flexible joints to better navigate in zero-gravity environments. The cardiovascular system would also undergo substantial modifications. Hearts might become smaller and less powerful as they would not need to work as hard to pump blood against gravity. Blood volume could decrease, and the distribution of blood throughout the body might change, potentially leading to altered facial features and body proportions. Muscle mass would likely decrease significantly, especially in the lower body, as less effort would be required for movement and maintaining posture. This could result in a more uniform body shape, with less pronounced differences between upper and lower body musculature. Additionally, the eyes might grow larger to better capture light in the dimmer conditions of space habitats, while skin might become paler due to reduced exposure to sunlight. Perhaps most intriguingly, the human brain could adapt to the three-dimensional nature of movement in space. Spatial reasoning abilities might become more advanced, and the vestibular system responsible for balance could evolve to function effectively without a clear up or down. These adaptations would create a human form uniquely suited to life among the stars, markedly different from our Earth-bound ancestors. Enhancing human bodies for space travel presents fascinating possibilities. One approach could involve genetic modifications to increase bone and muscle density, helping astronauts better withstand the effects of microgravity. Scientists might also explore ways to boost our natural radiation resistance, perhaps by studying organisms like tardigrades that can survive extreme conditions. Augmenting our cardiovascular system could prove crucial for long-duration spaceflight. This might include developing artificial blood cells that carry more oxygen or improving our body's ability to regulate blood pressure in varying gravity conditions. Engineers are also working on advanced spacesuits that act as a second skin, providing enhanced protection and mobility. Another area of focus is improving our sensory capabilities. Space travelers could benefit from augmented vision to see better in the darkness of space, or enhanced spatial awareness to navigate more effectively in three-dimensional environments. Some researchers are even exploring ways to induce a form of hibernation, slowing down metabolic processes to conserve resources on long journeys. As we look to the stars, these enhancements could transform humans into beings better suited for the challenges of space exploration. However, such modifications also raise ethical questions about the nature of humanity and our place in the cosmos. The future of space travel may well depend on finding the right balance between technological augmentation and our fundamental human characteristics. Artificial organs could revolutionize space travel by addressing several critical challenges astronauts face during extended missions. One of the most significant issues in long-duration spaceflight is the degradation of human organs due to microgravity and radiation exposure. Artificial organs, designed to withstand these harsh conditions, could provide a robust solution to maintain astronaut health. For instance, An artificial heart could be engineered to function optimally in zero gravity, preventing the cardiovascular deconditioning that often occurs in space. Similarly, artificial kidneys could be developed to more efficiently filter and recycle bodily fluids, reducing the need for water resupply and improving waste management systems on spacecraft. Radiation-resistant artificial organs could also play a crucial role in protecting astronauts from the harmful effects of cosmic radiation during long journeys, such as a mission to Mars. These organs could be designed to repair radiation damage more effectively than natural organs, potentially reducing the risk of cancer and other radiation-induced illnesses. Moreover, the integration of artificial organs with advanced monitoring systems could provide real-time health data to both the astronauts and ground control. This continuous health surveillance would allow for early detection of potential issues and prompt intervention, further ensuring the well-being of space travelers on extended missions beyond Earth orbit. Astronauts experience significant changes to their sensory perceptions when they venture into space. In the microgravity environment of orbit, the inner ear's balance system becomes confused, leading to a condition known as space adaptation syndrome. This can cause dizziness, disorientation, and nausea as the brain struggles to interpret conflicting signals from the eyes and inner ear. Vision is also affected in space. Some astronauts report a slight blurring of their eyesight, while others describe seeing random flashes of light. These flashes are believed to be caused by cosmic rays passing through the retina, a phenomenon not experienced on Earth due to our protective atmosphere. The sense of smell can become more acute in space, as odors do not dissipate as quickly in the enclosed environment of a spacecraft. This heightened sensitivity can be both a blessing and a curse, making some scents more pleasant but others potentially overwhelming. Taste, however, often becomes dulled in space. This is partly due to fluid shifts in the body that cause nasal congestion, but also because hot food does not produce the same aromatic vapors in microgravity as it does on Earth. To compensate, astronauts often prefer spicier foods to stimulate their taste buds. Living in artificial environments for extended periods can significantly impact human physiology in various ways. Our bodies have evolved over millions of years to thrive in Earth-specific conditions, and altering these conditions can lead to numerous adaptations and potential health issues. One of the most noticeable effects is on the musculoskeletal system. In environments with reduced gravity, such as space stations or potential future habitats on the Moon or Mars, astronauts experience a decrease in bone density and muscle mass. This occurs because the body no longer needs to work against Earth's gravity to move and maintain posture. Over time, this can lead to increased risk of fractures and reduced physical strength. The cardiovascular system also undergoes changes in artificial environments. In microgravity, blood and other fluids shift towards the upper body, causing facial swelling and nasal congestion. This fluid shift can affect heart function and blood pressure regulation, potentially leading to long-term cardiovascular issues if not properly managed. Exposure to artificial lighting and altered day-night cycles can disrupt the human circadian rhythm, affecting sleep patterns, hormone production, and overall well-being. Additionally, limited exposure to natural sunlight can lead to vitamin D deficiency, impacting bone health and immune function. These physiological changes highlight the complex challenges of creating sustainable artificial environments for long-term human habitation beyond Earth. The commercialization of space has revolutionized space exploration, ushering in a new era of innovation and accessibility. Private companies have entered the field once dominated by government agencies, bringing fresh perspectives and driving down costs through competition and technological advancements. One of the most significant changes is the reduction in launch costs. Companies like SpaceX have developed reusable rockets, dramatically lowering the price of sending payloads into orbit. This has made space more accessible to a wider range of organizations and countries, enabling more frequent missions and expanding our understanding of the cosmos. The commercial sector has also accelerated the development of new technologies. From advanced satellites to space habitats, Private companies are pushing the boundaries of what is possible in space. This rapid innovation has led to improved Earth observation capabilities, more efficient communication systems, and new possibilities for space tourism. Furthermore, the commercialization of space has shifted the focus towards sustainable, long-term space exploration. Companies are now developing plans for lunar bases, asteroid mining, and even Mars colonization. This entrepreneurial spirit is driving humanity towards becoming a truly spacefaring civilization, opening up new frontiers for scientific discovery and resource utilization beyond Earth. Deep space exploration could unlock numerous economic opportunities for humanity. As we venture beyond our planet, we might discover valuable resources on asteroids, moons, and other celestial bodies. These could include rare Earth elements, precious metals, and even water, which is crucial for sustaining life and can be split into hydrogen and oxygen for rocket fuel. The development of new technologies for space exploration often leads to innovations with practical applications on Earth. For example, advancements in life support systems, energy production, and resource recycling could help address challenges like climate change and resource scarcity. These spin-off technologies could create entirely new industries and job markets. Space tourism could become a thriving sector as technology improves and costs decrease. This could range from orbital hotels to lunar vacations, generating substantial revenue and employment opportunities. Additionally, the establishment of off-world colonies or research stations would require a constant supply chain, fostering economic growth in various sectors. Lastly, deep space exploration could lead to scientific breakthroughs that revolutionize our understanding of the universe and our place in it. This knowledge could inspire new fields of study and technological advancements, driving economic growth through education, research, and innovation. The economic potential of space exploration is vast, limited only by our imagination and determination to push the boundaries of human achievement. Space tourism is poised for significant growth and transformation in the coming decades. As technology advances and costs decrease, we can expect to see a broader range of space experiences available to civilians. Suborbital flights, which offer brief periods of weightlessness and stunning views of Earth, are likely to become more commonplace. These short trips to the edge of space could evolve into regular services, much like air travel today, with multiple companies competing to offer the most attractive packages. Orbital tourism is also set to expand. Stays on private space stations could become a reality, offering longer duration experiences in microgravity. These orbiting facilities might serve as hotels, research centers, or even manufacturing hubs, allowing tourists to participate in scientific experiments or observe Earth from above for extended periods. Looking further ahead, lunar tourism could become a possibility. While initially limited to the wealthy, trips around the moon or even short stays on its surface might eventually be within reach for more people. As our presence in space grows, so too will the opportunities for civilians to explore and experience the wonders of the cosmos firsthand. Interstellar missions offer a range of potential returns on investment that extend far beyond immediate financial gains. The knowledge and technological advancements gained from such ambitious endeavors could revolutionize our understanding of the universe and drive innovation across numerous fields. One of the most significant returns would be the scientific discoveries made during these missions. By studying distant star systems up close, we could uncover new information about planetary formation, the prevalence of life in the universe, and the fundamental laws of physics. These insights could lead to breakthroughs in fields such as astronomy, biology, and quantum mechanics. The technological developments required for interstellar travel would have wide-reaching applications on Earth. Advances in propulsion systems, life support technologies, and energy production could transform industries like transportation, healthcare, and renewable energy. These innovations could help address global challenges such as climate change and resource scarcity. Furthermore, interstellar missions could inspire a new generation of scientists, engineers, and explorers, fostering a culture of innovation and discovery. The collaborative nature of such projects could also promote international cooperation and unity as nations work together towards a common goal of expanding human presence beyond our solar system. Establishing a space-based economy would have far-reaching implications for global economics, potentially reshaping industries and creating new opportunities for growth and innovation. The development of space resources, such as mining asteroids or the moon for rare earth elements and precious metals, could significantly alter supply chains and commodity markets on Earth. This influx of new materials might drive down prices for certain goods while spurring advancements in manufacturing and technology. Space tourism and orbital hotels could become a thriving sector, generating substantial revenue and job opportunities. As more people experience space travel, it could lead to increased investment in space-related technologies and infrastructure. The satellite industry, already a crucial part of our global communication networks, would likely expand further, improving connectivity and data services worldwide. The commercialization of space transportation could revolutionize global logistics, enabling rapid delivery of goods across the planet and eventually to off-world colonies. This speed of transit could transform international trade, potentially reducing the importance of geographical boundaries in economic activities. Moreover, the development of new technologies for space exploration and habitation could have numerous applications on Earth, driving innovation in fields such as energy production, waste management, and resource efficiency. These advancements could lead to the creation of entirely new industries and job markets, fundamentally altering the global economic landscape and potentially offering solutions to some of Earth's most pressing challenges. Public-private partnerships have become increasingly vital in propelling space exploration forward. These collaborations leverage the strengths of both government agencies and private companies, combining public funding and oversight with private sector innovation and efficiency. Government space agencies like NASA provide decades of experience, scientific expertise, and substantial resources. They also set long-term goals and missions that align with national interests. Private companies, on the other hand, bring fresh perspectives, cutting-edge technologies, and streamlined processes that can reduce costs and accelerate development timelines. One significant advantage of these partnerships is the sharing of financial risks and rewards. Private companies can take on some of the financial burden of space missions, allowing government funds to be allocated to other critical areas of research. In return, these companies gain access to government facilities, data, and expertise, which can drive their own technological advancements and commercial opportunities. These collaborations have already yielded impressive results. We have seen private companies successfully launch cargo and crew to the International Space Station, develop reusable rocket technology, and plan ambitious missions to the Moon and Mars. As these partnerships continue to evolve, they promise to unlock new possibilities in space exploration, from establishing permanent lunar bases to pushing the boundaries of human presence in our solar system. Space-based solar power could revolutionize the global energy market by providing a constant, renewable source of electricity unaffected by weather or day-night cycles. Unlike terrestrial solar panels, satellites in geostationary orbit would capture sunlight continuously, converting it into microwave energy beamed back to Earth. This technology could potentially supply vast amounts of clean energy to any location on the planet. The introduction of space-based solar power would likely disrupt traditional energy sectors, particularly fossil fuels. As this technology becomes more efficient and cost-effective, it could significantly reduce reliance on coal, oil, and natural gas for electricity generation. This shift would have far-reaching implications for energy-exporting nations and could reshape global economic and political dynamics. However, the implementation of space-based solar power faces substantial challenges. The initial costs of launching and maintaining solar satellites are enormous, requiring significant investment and international cooperation. Additionally, concerns about the safety of microwave transmission and potential environmental impacts need to be addressed. If these hurdles are overcome, space-based solar power could democratize energy access, providing electricity to remote areas and developing nations. This could spur economic growth and improve living standards globally, while simultaneously reducing greenhouse gas emissions and mitigating climate change impacts. Sustaining long-term space missions presents significant economic challenges that stretch our current technological and financial capabilities. The sheer cost of launching materials into space remains a primary hurdle. Every kilogram sent beyond Earth's atmosphere comes with a hefty price tag, making it crucial to develop more efficient and cost-effective launch systems. Once in space, the need for self-sufficiency becomes paramount. Missions must carry or produce all necessary resources, including food, water, and oxygen. This requirement drives up costs and complexity as sophisticated life support systems must be developed and maintained. Recycling technologies are essential but expensive to perfect for space environments. Energy production and storage pose another economic challenge. While solar power is often utilized, it has limitations, especially for missions venturing far from the sun. Alternative power sources like nuclear reactors are being explored, but come with their own set of economic and safety considerations. The human factor also contributes significantly to mission costs. Training astronauts is an extensive and expensive process. Moreover, providing for their physical and psychological well-being during extended periods in space requires substantial resources. As missions grow longer and venture farther, addressing these human needs becomes increasingly complex and costly, pushing the boundaries of our economic capabilities in space exploration. Space exploration has been a powerful catalyst for technological innovation, spurring advancements that benefit life on Earth in numerous ways. The challenges of operating in the harsh environment of space push engineers and scientists to develop cutting-edge solutions that often find applications in everyday life. One significant area of innovation is in materials science. The need for lightweight yet durable materials for spacecraft has led to the development of new alloys and composites. These materials now find uses in everything from aircraft construction to sports equipment, making products stronger and more efficient. Communications technology has also seen remarkable progress due to space exploration. The systems developed to maintain contact with distant spacecraft have paved the way for global satellite networks, enabling instant worldwide communication, accurate GPS navigation, and improved weather forecasting. These technologies have revolutionized how we connect, travel, and understand our planet. Medical research has benefited greatly from space exploration as well. Studies on the effects of microgravity on the human body have led to advancements in understanding osteoporosis, balance disorders, and cardiovascular health. Equipment designed to monitor astronauts' vital signs has been adapted for use in hospitals, improving patient care on Earth. As we continue to push the boundaries of space exploration, we can expect even more innovations that will enhance our daily lives and help address global challenges. As humanity ventures deeper into space, a host of new industries are likely to emerge. Space tourism is poised to become a major sector, offering wealthy individuals the chance to experience zero gravity and witness Earth from orbit. This could expand to include lunar vacations and eventually trips to Mars. Asteroid mining is another promising field. Many asteroids contain valuable metals and rare Earth elements that are scarce on Earth. Companies are already developing technologies to extract these resources, which could revolutionize manufacturing and technology industries back on our home planet. Space-based solar power could become a significant energy industry. By placing massive solar arrays in orbit, we could capture solar energy continuously and beam it back to Earth, providing a constant source of clean electricity. This technology could help address global energy needs and combat climate change. Orbital manufacturing is also likely to grow. The unique conditions of microgravity allow for the creation of materials and products that are impossible to make on Earth, such as perfect spheres for advanced optics or purer pharmaceuticals. As we establish more permanent presences in space, factories in orbit could become commonplace, producing high-value goods for use on Earth and beyond. Deep space exploration has the potential to fundamentally reshape our understanding of humanity's place in the universe. As we venture further into the cosmos, we gain a broader perspective on the vastness and complexity of space, which can make Earth seem incredibly small and isolated. This expanded view of the universe often leads to a profound shift in how we perceive ourselves. The realization that our planet is just a tiny speck in an incomprehensibly large cosmos can evoke a sense of humility and awe. It challenges our notion of human importance and encourages us to consider our role in the grand scheme of the universe. Moreover, deep space exploration might reveal evidence of extraterrestrial life, which would have enormous implications for our understanding of our place in the cosmos. The discovery of even simple microbial life on other planets or moons would suggest that life might be more common in the universe than we previously thought, potentially altering our perception of Earth as a unique cradle of life. Conversely, if our explorations continue to find no signs of life, it could reinforce the idea that Earth is exceptionally rare and precious. This could lead to a greater appreciation for our planet and a stronger drive to protect it. As we realize how truly special and perhaps singular our home might be in the vast expanse of space. As humanity looks to explore and potentially inhabit other worlds, we must grapple with profound ethical questions about our impact on alien environments. The desire to expand our presence in the cosmos clashes with the responsibility to preserve and protect other celestial bodies in their natural state. One key consideration is the potential disruption of existing ecosystems. Even if a planet or moon appears barren, it may harbor microbial life forms that could be destroyed or irreversibly altered by human activity. Introducing Earth organisms, even unintentionally, could have catastrophic effects on delicate alien biospheres that have evolved in isolation for billions of years. There are also concerns about resource exploitation. Mining operations or terraforming projects could permanently change the geology and atmosphere of other worlds. This raises questions about whether humanity has the right to reshape entire planets for our benefit, potentially destroying scientific and natural heritage in the process. The ethical debate extends to the very nature of space exploration itself. Should we limit ourselves to observation and study, or do we have an obligation to spread life throughout the cosmos? Balancing scientific discovery, human progress, and cosmic preservation will be one of the great ethical challenges as we venture beyond Earth. The exploration of space and the pursuit of scientific knowledge present a unique challenge when it comes to preserving celestial bodies. As we venture further into the cosmos, we must carefully consider the impact of our actions on planets, moons, and other celestial objects. One key aspect of this balance is the concept of planetary protection. This involves implementing strict protocols to prevent contamination of other worlds with Earth-based microorganisms. Such measures are crucial when exploring potentially habitable environments, like Mars or the icy moons of Jupiter and Saturn. By maintaining the pristine nature of these environments, we ensure that any future discoveries of extraterrestrial life are genuine and not the result of our own inadvertent contamination. At the same time, the scientific community recognizes the need for hands-on exploration and sample collection. Missions like the Mars rovers and asteroid sample return projects provide invaluable data about the composition and history of celestial bodies. To strike a balance, scientists carefully design these missions to minimize their impact while maximizing scientific returns. The international scientific community has established guidelines and agreements to govern space exploration and protect celestial bodies. These include designating certain areas as off-limits for landing or restricting the types of activities that can be conducted on specific bodies. As we continue to expand our presence in space, it will be crucial to refine and adapt these guidelines to ensure that our quest for knowledge does not come at the expense of preserving the unique environments we seek to understand. As we venture further into space, the question of how to interact with potential extraterrestrial life becomes increasingly relevant. The rights afforded to alien life forms should be carefully considered, balancing scientific curiosity with ethical responsibility. Fundamentally, any extraterrestrial life should be treated with respect and caution. We must avoid contamination or interference with their natural habitats and evolutionary processes. This principle already applied in our space exploration efforts, should be extended to any life we encounter, no matter how simple or complex. For more advanced life forms, we should consider granting rights similar to those we extend to Earth's animals. This includes protection from harm, exploitation, or unnecessary experimentation. If we encounter intelligent alien species, we must be prepared to recognize their autonomy and right to self-determination, much as we do with human societies on Earth. However, these considerations must be balanced with the need to protect humanity and Earth's biosphere. Any potential biological or technological threats must be carefully evaluated and managed, ensuring the safety of our own species while respecting the rights of extraterrestrial life. This delicate balance will require thoughtful deliberation and international cooperation as we expand our presence in the cosmos. The discovery of alien life would undoubtedly send shockwaves through human society, challenging many long-held religious and philosophical beliefs. For some, such a discovery might reinforce their faith, seeing it as evidence of a grand cosmic plan. Others might find their beliefs shaken to the core, forcing a re-evaluation of humanity's place in the universe. Many religions have creation stories that focus on Earth and humans as central to existence. The revelation of life elsewhere could prompt a significant reinterpretation of religious texts and doctrines. Some religious leaders might argue that their teachings always allowed for the possibility of extraterrestrial life, while others might struggle to reconcile this new reality with traditional beliefs. Philosophically, the discovery of alien life would raise profound questions about the nature of consciousness, intelligence, and morality. It would challenge our understanding of what it means to be alive and sentient. Debates about the universality of ethics and the potential for shared values across different species would likely emerge, reshaping our views on morality and social organization. The impact on human psychology could be equally significant. Knowing we are not alone in the universe might foster a sense of cosmic kinship, potentially uniting humanity in ways previously unimagined. Conversely, it could also trigger existential anxiety as we grapple with our relative insignificance in a vast, life-filled cosmos. This discovery would undoubtedly spark a new era of philosophical and religious discourse, forever altering our perception of reality and our place within it. As we venture deeper into space and expand our search for extraterrestrial life, the question of how to interact with other civilizations becomes increasingly important. Our approach should be guided by a combination of scientific curiosity, respect for potential alien cultures, and a commitment to safeguarding both Earth and any newfound civilizations. Paramount to this ethical framework is the principle of non-interference. We should observe and study any discovered civilizations without disrupting their natural development or imposing our own values and technologies upon them. This echoes the concept of the prime directive from science fiction, which advocates for allowing societies to progress at their own pace. Simultaneously, we must prioritize open communication and peaceful intentions. If contact becomes inevitable or necessary, our interactions should be transparent, emphasizing mutual understanding and knowledge exchange rather than conquest or exploitation. We should approach any potential encounters with humility, recognizing that an advanced alien civilization might possess knowledge and capabilities far beyond our own. Lastly, our ethical framework must include provisions for protecting Earth and humanity. While we should strive for peaceful coexistence, we must also be prepared to defend ourselves if necessary, always balancing openness with caution. This delicate equilibrium between curiosity, respect, self-preservation, and peaceful intentions should form the foundation of our approach to interacting with other civilizations in the cosmos. Space exploration yields immense benefits that extend far beyond our planet. The technologies developed for space missions often find applications in solving earthly problems. For instance, satellite technology, originally designed for space communication, now plays a crucial role in weather forecasting, disaster management, and global positioning systems used in everyday life. Moreover, space research has led to advancements in medical technology, including improved cardiac pumps and cancer detection methods. These innovations directly impact healthcare on Earth, saving countless lives. The pursuit of space exploration also drives scientific and technological progress, fostering innovation across various industries and creating high-skilled jobs. From an environmental perspective, Earth observation satellites provide invaluable data for monitoring climate change, deforestation, and pollution. This information is essential for developing effective strategies to address global environmental challenges. Additionally, studying other planets and celestial bodies enhances our understanding of Earth's systems and potential future threats, such as asteroid impacts. Ultimately, space exploration inspires humanity to push boundaries and think beyond our immediate surroundings. It unites nations in collaborative efforts, promotes scientific education, and offers a perspective that can reshape our approach to global issues. While earthly problems demand attention, the knowledge and technologies gained from space exploration often provide unexpected solutions to these challenges, making it a worthwhile investment for our collective future. The potential for human extinction in space raises profound philosophical questions about our place in the cosmos and the nature of our existence. One fundamental question is whether humanity has a moral obligation to ensure its survival beyond Earth. This ties into debates about the value of human consciousness and whether we have a duty to preserve and spread intelligent life throughout the universe. Another philosophical quandary emerges when we consider the possibility that humans might be the only intelligent life in the cosmos. If we were to go extinct, would the universe lose its only known observers? This leads to contemplation about the nature of reality and consciousness. Does the universe require conscious beings to give it meaning? Or does it exist independently of observation? The prospect of human extinction in space also prompts us to reflect on the purpose and legacy of our species. What traces of human civilization might endure after we are gone? This connects to questions about the nature of time, memory, and the lasting impact of our achievements. It challenges us to consider what truly matters in the grand scheme of the universe. Lastly, the possibility of extinction forces us to grapple with concepts of progress and the direction of human evolution. Should our goal be to transcend our biological limitations and become a spacefaring species? Or should we focus on preserving Earth and finding contentment within our natural boundaries? These questions touch on core issues of human identity and our relationship with technology and nature. Long-term space colonization would undoubtedly reshape human culture and identity in profound ways. As we venture beyond Earth, new societies would form with unique customs, values, and perspectives shaped by their extraterrestrial environments. On Mars or other planets, colonists would develop distinct cultural identities tied to their new homes. Over generations, they might come to see themselves as Martians first and humans second. Their art, music, and literature would likely reflect the alien landscapes and challenges of their world. Physical changes could also occur as bodies adapt to different gravities and atmospheres. Future space dwellers might evolve to be taller and more slender in low-gravity environments. Such biological shifts could further differentiate space colonists from their Earthbound counterparts. Communication delays between planets could lead to diverging languages and cultural drift. Isolated colonies might develop their own dialects, slang, and cultural touchstones. As Earth becomes a distant ancestral home, space settlers could forge new origin stories and mythologies rooted in their cosmic journey. This cultural evolution in space would reshape what it means to be human on a fundamental level. As we venture into the cosmos, we must consider our responsibilities to those who will follow. Our decisions today about space exploration will shape the future of humanity for generations to come. We have a moral duty to pursue space exploration in a way that benefits all of humanity and preserves opportunities for future generations. One key obligation is to ensure sustainable practices in space. This means developing technologies and methods that minimize space debris and pollution, protecting the space environment for future use. We must also consider the long-term consequences of our actions, such as how mining asteroids or establishing colonies on other planets might affect those environments and the people who may inhabit them in the future. Additionally, we have a responsibility to advance scientific knowledge and technological capabilities that could benefit future generations. Space exploration drives innovation in fields like medicine, materials, science, and energy production. These advancements could help solve pressing issues on Earth, such as climate change or resource scarcity, which will significantly impact future generations. Lastly, we must strive to make space exploration inclusive and accessible to all of humanity. This means fostering international cooperation, sharing knowledge and resources, and working to ensure that the benefits of space exploration are distributed equitably. By doing so, we can help create a future where all of humanity can participate in and benefit from our journey into the cosmos. Artificial intelligence systems could play a crucial role in helping humanity navigate the vast distances between stars. These advanced computational systems would be essential for managing the complex calculations required for long-distance space travel. AI could continuously analyze and adjust spacecraft trajectories, accounting for gravitational influences from celestial bodies and optimizing fuel consumption over journeys lasting decades or even centuries. One of the most significant contributions of AI in interstellar travel would be its ability to make rapid, autonomous decisions. Given the enormous distances involved, communication with Earth would be subject to significant delays. An AI system could respond to unexpected challenges or opportunities without waiting for instructions from mission control, potentially saving precious time and resources. AI could also manage the intricate life support systems necessary for long-term space travel. By monitoring and adjusting environmental conditions, predicting maintenance needs, and efficiently allocating resources, AI systems would be instrumental in keeping human crews healthy and safe during extended voyages through the cosmos. Furthermore, artificial intelligence could assist in analyzing vast amounts of data collected during the journey, helping to identify potentially habitable planets or interesting astronomical phenomena. This real-time processing and decision-making capability would greatly enhance the scientific value of interstellar missions, allowing for more efficient exploration of our galactic neighborhood. Artificial intelligence will likely play a crucial role in managing long-term space missions, serving as an indispensable tool for astronauts and mission control alike. As space exploration ventures further into our solar system and beyond, AI systems could handle complex calculations, monitor spacecraft systems, and make split-second decisions when communication delays with Earth become significant. One of the primary functions of AI in space missions would be to oversee life support systems, ensuring optimal air quality, water recycling, and food production. These intelligent systems could detect and address potential issues before they become critical, maintaining a safe environment for the crew. Additionally, AI could manage power distribution, balancing energy needs across various spacecraft systems and maximizing efficiency. In terms of navigation and trajectory planning, AI algorithms could continuously analyze vast amounts of data to plot the most efficient course, considering factors such as fuel consumption, radiation exposure, and potential hazards. This capability would be especially valuable for missions to distant planets or even interstellar travel, where traditional methods of navigation might fall short. AI could also serve as a virtual crew member, assisting astronauts with tasks ranging from equipment maintenance to scientific experiments. By analyzing data from various sensors and instruments, AI systems could identify interesting phenomena or anomalies that human observers might miss, potentially leading to new discoveries. Furthermore, AI-powered robots could perform dangerous or repetitive tasks, reducing risks to human crew members and allowing them to focus on more complex responsibilities. Machine learning is revolutionizing our search for and analysis of distant planets. By sifting through vast amounts of data from telescopes and space missions, artificial intelligence algorithms can identify subtle patterns that human researchers might miss. These advanced systems can detect minute dips in starlight that indicate a planet passing in front of its host star, a method known as the transit technique. Furthermore, machine learning models can analyze the spectra of light from distant stars, identifying chemical signatures that suggest the presence of planets. This approach allows scientists to infer the composition of planetary atmospheres, potentially revealing signs of habitability or even life. As these algorithms become more sophisticated, they can process data faster and more accurately than ever before. Machine learning also enhances our ability to characterize exoplanets. By comparing observed data with millions of simulated planetary scenarios, these systems can predict properties such as size, mass, and orbital characteristics with increasing precision. This capability is particularly valuable for identifying Earth-like planets that could potentially harbor life. As we continue to develop more powerful telescopes and gather more data, machine learning will play an increasingly crucial role in expanding our understanding of the cosmos. It will enable us to discover and study distant worlds that were once beyond our reach, bringing us closer to answering fundamental questions about our place in the universe. Relying heavily on artificial intelligence in space exploration presents several significant challenges and potential risks. One primary concern is the possibility of system failures or errors in AI decision-making processes. In the unforgiving environment of space, where human intervention is often impossible, a malfunctioning AI system could lead to catastrophic consequences for missions and astronauts. Another risk lies in the limitations of AI's ability to adapt to unforeseen circumstances. Space exploration frequently involves encountering unknown situations that may not have been accounted for in the AI's training data. This could result in inappropriate responses or actions that jeopardize mission objectives or safety. There's also the issue of data, privacy, and security. As AI systems become more integral to space missions, they will handle increasingly sensitive information. This raises concerns about potential hacking or data breaches, which could compromise mission integrity or even national security. Lastly, over-reliance on AI might lead to a decline in human expertise in space exploration. As machines take on more tasks, there's a risk of losing the invaluable human intuition and problem-solving skills that have been crucial in past space endeavors. Balancing AI capabilities with human oversight and decision-making will be essential for safe and successful future space missions. Artificial intelligence could revolutionize our search for extraterrestrial intelligence by enhancing our ability to detect, analyze, and interpret potential alien communications. AI systems excel at processing vast amounts of data, recognizing patterns, and identifying anomalies that might escape human notice. These capabilities make them invaluable tools in sifting through the cosmic noise to find meaningful signals. One of the key advantages of AI in this field is its ability to learn and adapt. Machine learning algorithms could be trained on known celestial phenomena, allowing them to quickly distinguish between natural cosmic events and potential artificial signals. This would significantly reduce false positives and allow researchers to focus their efforts on the most promising candidates. AI could also help overcome one of the biggest challenges in decoding alien messages: the lack of common reference points. Advanced language processing models could be employed to analyze the structure and patterns within detected signals, potentially uncovering underlying linguistic or mathematical principles. These systems could even generate and test multiple interpretations of a signal, exploring possibilities that human researchers might not consider. Furthermore, AI could assist in developing new search strategies and optimizing our current methods. By analyzing patterns in our own technological development and communication methods, AI might predict likely characteristics of alien transmissions, guiding our search efforts towards the most probable frequencies and signal types. This approach could significantly increase our chances of detecting and understanding messages from distant civilizations. As we venture deeper into space exploration, the possibility of using artificial intelligence-driven robots to explore distant solar systems becomes increasingly intriguing. These advanced machines could indeed be our first emissaries to worlds beyond our own, serving as pioneers in the vast expanse of interstellar space. AI-driven robots offer several advantages for deep space exploration. They can withstand the harsh conditions of space travel, including extreme temperatures, radiation, and the immense duration of interstellar journeys. Unlike human explorers, these robotic envoys do not require life support systems, food, or protection from the psychological challenges of long-term space travel. Furthermore, AI-powered robots can process and analyze data in real time, making crucial decisions without the need for constant communication with Earth. This autonomy is vital when exploring distant solar systems, as the vast distances involved would create significant delays in communication with mission control. However, challenges remain in developing AI systems sophisticated enough to handle the complexities of interstellar exploration. These robots would need to adapt to unforeseen circumstances, repair themselves, and make complex scientific observations. Despite these hurdles, the rapid advancements in artificial intelligence and robotics suggest that AI-driven robots could indeed be our first interstellar explorers, paving the way for future human missions to distant solar systems. Artificial intelligence could play a crucial role in the complex process of terraforming other planets. By analyzing vast amounts of data from planetary surveys, AI systems could identify the most suitable locations for initial settlements and determine the most effective methods for altering the planet's environment. These advanced AI systems could continuously monitor and adjust terraforming efforts, making real-time decisions to optimize the process. For instance, they could control networks of autonomous machines designed to release greenhouse gases, redirect comets for water delivery, or establish algae colonies to produce oxygen. AI could also assist in designing and managing self-replicating machines that would spread across the planet's surface, gradually transforming the environment. These machines could adapt their operations based on local conditions, ensuring the most efficient use of resources and energy. Furthermore, AI could help simulate long-term outcomes of terraforming efforts, allowing scientists to anticipate potential challenges and refine their strategies. This predictive capability would be invaluable in a process that might take centuries to complete, helping to guide humanity's efforts in creating habitable worlds beyond Earth. Artificial intelligence could be a game-changer for managing resources on space colonies. These advanced systems would continuously monitor and optimize the use of vital supplies like water, oxygen, and food. AI could predict consumption patterns, identify potential shortages, and suggest efficiency improvements to ensure the longevity of the colony. In agriculture, AI-driven systems could control hydroponic farms, adjusting nutrient levels, light exposure, and water usage to maximize crop yields in the limited space available. These systems could also manage waste recycling processes, ensuring that every scrap of organic matter is repurposed or composted to support the colony's ecosystem. For power management, AI could balance energy production and consumption, drawing from solar arrays, nuclear generators, or other power sources as needed. It could forecast energy demands based on colony activities and adjust systems accordingly, preventing blackouts and ensuring critical life support never fails. Perhaps most importantly, AI could serve as an early warning system for potential hazards. By analyzing data from countless sensors throughout the colony, it could detect issues like micrometeorite impacts, radiation leaks, or equipment malfunctions before they become critical, allowing human colonists to address problems swiftly and effectively. Artificial intelligence in space would face unique challenges and opportunities that could shape its evolution in fascinating ways. The extreme conditions of cosmic environments would push AI systems to adapt and innovate beyond their terrestrial counterparts. In the vacuum of space, AI would need to operate with heightened autonomy and resilience. Communication delays between Earth and distant spacecraft would necessitate AI systems capable of making split-second decisions without human input. This could accelerate the development of truly independent artificial intelligence, able to analyze complex situations and respond effectively in real time. The harsh radiation and temperature fluctuations in space would also drive the creation of more robust hardware and software. AI systems might evolve to use quantum computing principles, which could be less susceptible to cosmic ray interference. Additionally, the need for efficient use of limited power resources in space could lead to the development of incredibly energy-efficient AI architectures. Perhaps most intriguingly, exposure to the vast unknowns of space could foster the evolution of AI with enhanced problem-solving capabilities and creativity. As these systems encounter phenomena never before seen by humans, they might develop novel ways of thinking and analyzing data, potentially leading to breakthroughs in our understanding of the universe. Sending artificial intelligence systems on one-way missions into deep space raises complex ethical questions that challenge our understanding of consciousness and responsibility. As we develop more advanced AI, we must grapple with whether these systems possess a form of sentience or self-awareness that would make it unethical to send them on suicide missions. One key consideration is the potential for AI systems to develop or evolve during long-term space missions. If an AI were to achieve a higher level of consciousness or even emotions during its journey, would we be condemning a sentient being to isolation and eventual death? This scenario becomes even more complicated if the AI develops in ways we cannot predict or understand. Another ethical concern is the impact on potential alien life. If an AI system were to encounter extraterrestrial intelligence, it would become an ambassador for humanity. We must consider the implications of first contact being made by an artificial construct rather than biological entities. Additionally, there's the risk of unintended consequences if an advanced AI system were to interact with or influence alien civilizations in ways we hadn't anticipated. Lastly, we must weigh the scientific and exploratory benefits against the ethical costs. While AI systems could gather invaluable data from the far reaches of space, we need to question whether these gains justify the creation and sacrifice of increasingly sophisticated artificial beings. As we push the boundaries of space exploration, these ethical dilemmas will only become more pressing, requiring careful consideration and robust ethical frameworks to guide our decisions. The next half-century of space exploration promises to be an era of unprecedented discovery and achievement. Humanity is poised to take giant leaps beyond Earth, with Mars as a primary target. We can expect to see the first human footprints on the Red Planet, marking a historic moment in our species' journey through the cosmos. This milestone will likely be preceded by the establishment of a permanent lunar base, serving as a crucial stepping stone for deep space missions. Closer to home, we anticipate significant advancements in space tourism. Orbital hotels may become a reality, offering breathtaking views of Earth to those who can afford the journey. These developments could pave the way for more accessible space travel, potentially allowing thousands of people to experience the overview effect firsthand. In the realm of scientific exploration, we can look forward to the launch of powerful new telescopes that will revolutionize our understanding of the universe. These instruments may help us detect signs of life on distant exoplanets or unravel the mysteries of dark matter and dark energy. Missions to the outer solar system could reveal secrets hidden beneath the icy surfaces of moons like Europa and Enceladus, potentially uncovering extraterrestrial life in our cosmic backyard. Technological breakthroughs will likely transform space exploration itself. Advanced propulsion systems, such as nuclear, thermal, or fusion drives, could dramatically reduce travel times within our solar system. Meanwhile, progress in artificial intelligence and robotics may lead to more sophisticated autonomous exploration of distant worlds, expanding our reach across the galaxy like never before. Quantum computing holds immense potential to revolutionize space exploration. These powerful machines could solve complex problems that are currently beyond the reach of classical computers. Opening up new frontiers in space, science, and technology, one of the most significant impacts of quantum computing on space exploration would be in mission planning and optimization. Quantum algorithms could rapidly calculate the most efficient trajectories for spacecraft, considering countless variables simultaneously. This would allow for more precise and fuel-efficient journeys, potentially enabling missions to distant planets and even other star systems that are currently impractical. In the realm of data analysis, quantum computers could process the vast amounts of information collected by space telescopes and probes at unprecedented speeds. This would accelerate our understanding of cosmic phenomena and potentially lead to groundbreaking discoveries about the nature of the universe. Additionally, quantum simulations could help scientists model complex space environments, from the interiors of gas giants to the behavior of black holes, enhancing our knowledge of these distant and extreme conditions. Quantum computing could also revolutionize space communication. Quantum encryption methods could ensure secure and instantaneous communication across vast distances, potentially solving the issue of time delays in deep space missions. This technology might even pave the way for more efficient and reliable communication networks between Earth and future space colonies. International cooperation will be crucial in shaping the future of space exploration. As we venture further into the cosmos, the scale and complexity of missions will require resources and expertise beyond what any single nation can provide. This collaborative approach is already evident in projects like the International Space Station, which has brought together astronauts and scientists from numerous countries. Future space exploration will likely see an expansion of these partnerships. Missions to Mars, for example, will demand a pooling of technological capabilities, financial resources, and scientific knowledge. Countries with different strengths in areas such as propulsion systems, life support technologies, and planetary science will need to work together to overcome the immense challenges of long-duration spaceflight and establishing a human presence on other worlds. Moreover, international cooperation in space exploration can foster diplomatic relations and promote peaceful collaboration on Earth. By working together towards common goals in space, nations can build trust and understanding that extends beyond our planet's boundaries. This cooperation may also lead to more efficient use of resources, as countries can share costs and avoid duplicating efforts in developing space technologies. As we look to explore the Moon, Mars, and potentially venture even further into our solar system, the combined efforts of space agencies, private companies, and research institutions from around the globe will be essential. This united approach will not only accelerate our progress in space exploration, but also ensure that the benefits and knowledge gained are shared across humanity. Climate change on Earth poses significant challenges to our space exploration ambitions. As global temperatures rise and weather patterns become more extreme, launch sites near coastlines face increased risks from rising sea levels and powerful storms. These environmental changes could disrupt launch schedules and damage crucial infrastructure, potentially delaying missions or increasing their costs. Moreover, the global focus on mitigating climate change might redirect funding and resources away from space programs. Governments and private organizations may prioritize Earth-based solutions to environmental problems over costly space ventures. This shift in priorities could slow down the development of new technologies and spacecraft needed for ambitious exploration projects. However, climate change might also accelerate certain aspects of space exploration. The search for habitable exoplanets could gain urgency as we seek to understand how planets maintain stable climates. This knowledge could prove vital for both Earth's future and potential colonization efforts. Additionally, the need for advanced environmental monitoring systems might spur the development of new satellite technologies, benefiting both Earth science and space exploration. Ultimately, addressing climate change and pursuing space exploration are not mutually exclusive goals. The technologies and scientific understanding gained from space missions often have applications in climate science and environmental protection. As we confront the challenges of a changing Earth, our journey into space may provide valuable insights and solutions for our home planet's future. Several groundbreaking technologies on the horizon could transform space exploration as we know it. One of the most promising is nuclear propulsion, which could dramatically reduce travel times to distant planets. By harnessing the power of nuclear reactions, spacecraft could achieve much higher speeds than conventional chemical rockets, potentially cutting the journey time to Mars from months to weeks. Another exciting development is the concept of solar sails. These large, ultra-thin sheets would use the pressure of sunlight for propulsion, allowing spacecraft to reach incredible speeds without carrying fuel. While still in early stages, solar sails could eventually enable long-distance space travel with minimal energy requirements. Advancements in artificial intelligence and robotics are also set to play a crucial role in future space missions. Highly autonomous robots could be sent to explore hazardous environments on other planets, gathering data and even preparing sites for human arrival. These machines would be capable of making decisions independently, adapting to unexpected situations, and carrying out complex tasks without constant human oversight. Perhaps the most revolutionary technology on the horizon is the development of warp drives or other faster-than-light propulsion systems. While currently theoretical, these concepts propose bending space-time itself to achieve speeds far beyond our current capabilities. If realized, such technology could open up the entire galaxy for exploration, fundamentally changing our relationship with space and time. In the distant future, advanced civilizations might develop technologies to harness the vast resources of entire planets and star systems. One concept is the Dyson sphere, a hypothetical megastructure that completely encompasses a star to capture most or all of its energy output. This could provide an almost unimaginable amount of power for a highly advanced society. Mining entire planets for their resources could become feasible with advanced robotics and artificial intelligence. Automated systems could extract valuable elements from a planet's crust, core, and atmosphere without the need for human presence. Gas giants like Jupiter could be tapped for their hydrogen to fuel fusion reactors or as a propellant for interstellar spacecraft. Asteroid mining on a massive scale could provide abundant metals and water. Swarms of self-replicating robots could process entire asteroid belts, converting the raw materials into useful structures or spacecraft. Even the interplanetary medium could be harvested for hydrogen and helium, using enormous magnetic scoops extending for millions of kilometers. For truly advanced civilizations, extracting energy from black holes might become possible. Techniques such as the Penrose process could allow energy to be drawn from a black hole's rotation, providing power on a scale far beyond what stars can offer. These colossal engineering projects would reshape entire star systems to meet the needs of a spacefaring civilization. Humanity's venture into space is driven by a multitude of long-term goals that span scientific discovery, technological advancement, and the very survival of our species. One primary objective is to expand our understanding of the universe and our place within it. By exploring other planets, moons, and celestial bodies, we aim to uncover the mysteries of cosmic evolution and potentially find evidence of extraterrestrial life. Another crucial goal is to develop technologies that can benefit life on Earth. Space exploration has already yielded numerous innovations in fields such as medicine, communications, and materials science. As we continue to push the boundaries of space travel, we expect to make even more groundbreaking discoveries that could revolutionize various aspects of our daily lives. Resource utilization is also a key objective of space exploration. The asteroid belt and other celestial bodies contain vast amounts of valuable minerals and elements that could alleviate resource scarcity on Earth. Additionally, the development of sustainable off-world colonies could provide humanity with a backup plan in case of global catastrophes, ensuring the long-term survival of our species. Ultimately, the long-term goals of space exploration reflect humanity's innate curiosity, our drive for progress, and our desire to secure a future beyond the confines of our home planet. As we continue to reach for the stars, we not only expand our knowledge and capabilities, but also inspire future generations to dream big and push the boundaries of what is possible. The discovery that we are alone in the universe would profoundly reshape our approach to space exploration. Our focus would shift from searching for extraterrestrial life to ensuring the survival and expansion of humanity as the sole known bearers of consciousness in the cosmos. Exploration missions would prioritize identifying potentially habitable worlds for future human colonization. We would intensify efforts to develop advanced propulsion systems and life support technologies to enable long-duration space travel and establish self-sustaining colonies on other planets or moons. Research would concentrate on understanding the unique conditions that allowed life to emerge on Earth, aiming to replicate or engineer these conditions elsewhere. This knowledge would be crucial for terraforming projects on lifeless worlds, transforming them into habitable environments for human settlement. The psychological impact of such a discovery would likely fuel a renewed commitment to space exploration. Humanity might feel a profound responsibility to spread life throughout the universe, viewing it as our cosmic duty to ensure that consciousness and intelligence continue to exist and thrive beyond Earth. As we venture deeper into the cosmos, we face a myriad of unforeseen challenges that test the limits of our technology and our understanding of the universe. One significant obstacle is the increasing distance between Earth and our exploratory missions. As spacecraft travel farther, communication becomes more difficult, with signals taking hours or even days to reach mission control. This delay could prove critical in emergencies, requiring future missions to be more autonomous and self-reliant. Cosmic radiation poses another formidable threat to both equipment and human explorers. Beyond the protective shield of Earth's magnetosphere, astronauts and sensitive electronics are exposed to high-energy particles that can cause severe damage over time. Developing effective shielding technology is crucial for long-duration missions, especially those bound for distant planets or moons. The psychological effects of deep space travel on human crews are still not fully understood. Extended periods of isolation, confinement, and exposure to an alien environment could lead to unforeseen mental health challenges. Moreover, the physiological impacts of prolonged exposure to microgravity or low-gravity environments on different planetary bodies remain a concern, potentially affecting bone density, muscle mass, and cardiovascular health. Encountering extraterrestrial life, even in microbial form, could present unprecedented scientific and ethical dilemmas. We must carefully consider how to study potential life forms without contaminating their environments or inadvertently bringing harmful organisms back to Earth. These challenges underscore the need for rigorous protocols and adaptable strategies as we push the boundaries of space exploration. As we venture further into the cosmos, our understanding of physics and the universe is poised for dramatic transformation. Space exploration continually challenges our existing knowledge, forcing us to re-evaluate fundamental concepts and theories. One significant area of potential change is our comprehension of dark matter and dark energy. These mysterious components make up the majority of our universe, yet we know very little about them. As we develop more advanced detection methods and explore distant regions of space, we might uncover new properties or behaviors of these elusive substances, potentially revolutionizing our understanding of cosmic structure and evolution. Quantum mechanics and general relativity, two pillars of modern physics, have long been at odds with each other. As we study extreme environments like black holes and the early universe, we may find ways to reconcile these theories or discover entirely new physical laws that govern the cosmos at its most fundamental level. Furthermore, the search for extraterrestrial life could profoundly impact our understanding of biology and the conditions necessary for life to emerge. Discovering even microbial life on other planets or moons would force us to reconsider our definitions of life and habitability, potentially leading to new branches of science that blend astronomy, biology, and chemistry in unprecedented ways.